this hall last year, and the year before that, there was acted out an extraordinary long-running drama that was one attempt to make the right decision about a complex scientific and technical subject. This is the Maltings at Snape in Suffolk, home of the Sizewell inquiry into the building of a nuclear power station on a site not very far from here. And in this hall, effectively, nuclear power was put on trial. It's empty now, but at the height of the inquiry, this stage was packed with QCs and lawyers, civil servants, Greenpeace, Friends of the Earth, scientists and engineers. It was the biggest single examination of the science and technology of nuclear power and the implications and effects of the radiation it causes there's ever been. The result was a vast accumulation of the facts, enough documents to fill a church hall, 16 million words. But this is a subject, unquestionably, in which the facts by themselves are not enough. It carries an immense emotional charge. And 6 weeks or so ago, the name Chernobyl flashed around the world to serve as a focus, a lightning conductor, if you like, for that emotional charge. Now, what happened at Chernobyl was a catastrophe of the very first magnitude for the people who died and will go on dying from the radiation that was released. The question is, was that catastrophe the beginning of the end for nuclear power? And even as the dust from Chernobyl continues to settle, so new nuclear power stations are being commissioned around the world. 2 of them are in the UK. Well, this is the very heart of Britain's latest nuclear power station, now almost completed on the east coast of Scotland near Torness. And in a matter of months, where I am standing now will become one of the most hostile environments on Earth, because we're right inside the pressure vessel that will house the core of the nuclear reactor itself. When they've inserted the uranium fuel into these guide tubes and switched the reactor on, then no one will ever venture into this space again, because it will become so searingly hot and so intensely radioactive that to do so would mean instant death. Now, for many people, that is the image they hold of the nuclear power industry in general, that it poses a constant and barely contained threat to human life and health. But is that a valid image? Well, in the light of what happened at Chernobyl, many people, perhaps a majority, would say unquestionably yes. But in this series, we shall in a sense be going back to square one, to examine the basis of nuclear power, the nature of the radiation that it creates, and the threat that it poses. Now, there is a widely held belief that we are somehow still on the threshold of the nuclear age, that it would, that is, be a relatively simple matter to switch nuclear power off. In fact, it's now over 30 years since nuclear electricity first flowed into people's houses in Russia, Great Britain and America. And by 1960, the number of commercial reactors had grown to 17. Over the next 15 years, the number of reactors around the world grew by more than 500%, from 90 in 1970 to 255 in 1980. And there are now over 370 reactors in 26 different countries. So, however you look at it, whatever the debate, whatever the fears and the hostilities, it does seem as if many countries are profoundly committed to a nuclear future. To force the nuclear genie back into the bottle would be very difficult indeed. And yet the deep unease and the distrust are perhaps stronger than ever, fueled by what have been called the willful ignorance of the public and the woeful inadequacies of us in the media. In fact, the general attitude to nuclear power is more complex than you might perhaps expect. We commissioned the University of Surrey to help us find out what a typical cross-section of the British public thought about nuclear power. They carried out 2 surveys for us, one in January and another just a few weeks ago after Chernobyl.
Thank you very much indeed. With respect to civil use of technology, nuclear technology such as making electricity, how much thought, if any, have you given to this issue?
Well, as long as it doesn't sort of cause any damage, I suppose it's okay, you know. I mean, you mean sort of nuclear energy, yes.
But yeah.
Well, I mean, some people say it can be bad, and I really don't know. I'm not sort of sufficiently well up in that, I'm afraid.
Well, as long as it can be controlled, the radioactivity controlled, then it doesn't worry me.
Until they find some definite way of either reusing or destroying the waste without endangering everybody else, yeah.
There's a few programmes on about all this stuff escaping, all the radioactivity escaping and everything, but, you know, I'm not against that at all. So that could be come by sort of things.
Right. Do you worry about that at all?
No, because I don't live near an area really, apart from Watermaster.
Now, thinking about other ways of making use of nuclear technology, such as a power station, is that something you ever think about at all?
No.
Anything that you're particularly interested in?
No.
So it's all something that's out there and happens
That's it, yeah.
somewhere else. And is that something that worries you at all?
No.
Before Chernobyl, roughly 1 in 4 thought that nuclear power stations were dangerous. In May, in response to Chernobyl, that figure had gone up to 39%. In January, 29% said they were worried to some extent. In May, after Chernobyl, that figure had gone up to 41%. But that still leaves more than half the population apparently not seriously concerned about nuclear power, even after as damaging an event as Chernobyl. Now, what are we to make of figures like this?
When you look at the kinds of things that worry people, if you ask them in an open-ended sort of way, as we've done in a number of surveys, what are the kinds of things that worry you, they will nominate very personal sorts of concerns. We live very complex lives. There are many things that are going on, and the things that actually make you lose sleep are whether there's employment in the family, whether there's illness in the family, very personal sorts of things. People very rarely nominate broader issues like nuclear energy as something that disturbs them in that very personal sort of way. If, however, you put a list of things for people to check off which of those worry you, then nuclear power zooms to the top.
Have you any idea what an atom is?
Yes. Well, probably like most people, you know. I'm not an expert, but I have an idea.
What do you think it is?
We also tried to measure people's knowledge of nuclear science and technology by asking them about the meaning of terms like atom and fission and meltdown.
I can't answer that one.
You've got no idea at all?
No, I've got no idea.
And
We then showed these results to 2 Harwell scientists for their comments.
familiar to you?
The scientists were actually quite surprised, I think, at the extent of knowledge that people had. And I concluded, in fact, that by and large, the population, if you had a group of people together in a room, they'd be able to piece something together that would give them some understanding of the issues. Any one individual is not likely to have access to all those pieces of information. So collectively, people do have a greater understanding than I think it is generally appreciated.
And what does the term radiation mean?
All the alpha, beta and gamma rays.
From?
The block of uranium or plutonium or bomb.
I don't know.
It's unseen energy.
Yes.
Which passes through you and bounces off you and goes around you.
Radiation. Well, it would be a big explosion and will it be burning?
It's what happens when the bomb goes off. It's like the stuff of the bomb burns your neck, layers of got.
And what would you be able to see it or?
Yeah, it's like snow, isn't it? It's like white flakes. And it gets all cold. It's hot radiation. Is it? Yeah, if it burns you, it's sort of radioactive, isn't it? Yeah. It's radioactive.
So it's clear that as a nation, we've acquired a pretty patchy knowledge of nuclear science and technology. And although we may laugh at some of those answers, if we put the same questions to a fair few scientists even, and more than a handful of journalists, we get the same sort of responses. And the problem is that in this country, there's not so much a debate going on as a confused battle, with the pro and the anti-nuclear factions constantly restating their positions, while the poor Joe public is left in the middle, getting more and more confused. And this industry itself, which would seem to have most to gain from promoting a free and open exchange of information, has in the past miserably failed to do so. So now, when it looks for support, it finds only alienation and mistrust. And it's clear that, certainly in the post-Chernobyl climate, any decision on the nuclear power industry is going to take much more into account than facts and figures and costs and benefits. The emotions just will not be set aside. In an industry as jargon-ridden as this one, and as so profoundly based on technology, some understanding of the science can only help. Everything in the universe is made of collections of atoms. These are the basic building blocks. No one has ever seen an atom, but they're visualized by scientists as very small, slightly fuzzy spheres. At the very center of each sphere, occupying perhaps 100 millionth of its volume, is an even smaller particle, the nucleus, and it's responsible for all the strange phenomena of nuclear physics, from radioactivity to the chain reaction. Now, the nucleus itself is also made up of different particles. The simplest atoms have only a few particles. Hydrogen, for example, has 1, and helium has 4. The key point is that every substance in the universe has a nucleus that's made up of 2 types of particles, called protons and neutrons. Nearly all the properties that we associate with different substances, such as hardness or lightness, or colour or taste, come simply from the different numbers of particles in the nucleus. Each different type of atom is known as an element, and these simple numerical differences in the number of protons and neutrons can lead to very dramatic effects. Now, one of them is that as the nuclei get heavier, some elements, particularly uranium for example, become unstable. It's as if they're unable to settle down with the jostling mass of 235 protons and neutrons that are crammed into the nucleus. Every now and then, one atom will behave oddly. It will throw off a clump of 4 particles, which are known together as an alpha particle, and it also emits a burst of gamma radiation. This property we call radioactivity, and it produces radiation. There are 4 different kinds of radiation. Alpha particles are quite heavy on the nuclear scale, but they only travel a few centimetres in air. They can't penetrate the skin, and they can be stopped by even a sheet of paper. But if you breathe in an alpha-emitting substance, these heavy particles can do a tremendous amount of damage to the cells they plough through. Beta particles, however, pose a threat both inside and outside the body. They're much smaller and travelling at much higher speeds. They can easily rip through the skin. However, they can be stopped by a few millimetres of plastic, or a sheet of glass, and even by a layer of water. The 2 other forms of radiation, gamma rays and neutrons, are by far the most difficult to shield against. Gamma radiation comes in the form of rays, rather like X-rays, while neutrons are heavy particles with enormous energy. They can both penetrate most substances, including the human body, causing immense damage to cells as they do so. To stop them, you need several centimetres of lead, at least 1.5 metres of special glass, as in these remote handling cells at Harwell, or several metres of solid concrete, which make up, for example, the biological shield that's wrapped around every nuclear core. But the fundamental point is that with the exception of neutrons, all these forms of radiation exist not only in the laboratory and the power station, they're all around us, as part of the natural environment. The basic problem, of course, as it's so often been said, is that we can't see or feel or taste or smell radiation. One of the reasons, perhaps, why it arouses so many fears. But that we are all constantly subjected to natural background radiation is unquestioned. Here in Somerset, for example, I'm getting about the average dose for the nation as a whole, rather more in Cornwall, rather less in parts of East Anglia. And to put a figure on that, one estimate is it amounts to 15,000 particles a second striking the body every second of every day, coming from the rocks and soil and cosmic rays from outer space, nothing at all to do with nuclear power. In the UK, for example, as in most other parts of the world, about 80% of all the radiation we're exposed to comes from these natural sources, as opposed to less than 1% that comes from the nuclear power industry. But the natural background level varies widely across the country. In general, the darker the shading on the map, the higher the average background radiation. But there are 3 or 4 hotspots where the background levels are several times higher than, say, in the southeast. These are the largely granite areas of Devon and Cornwall, Wales, Yorkshire and eastern Scotland. Now, when the radiation cloud swept across the country from Chernobyl, it added about 1/25 to the total background radiation for the year as a whole. And as for the longer-lived elements from Chernobyl that remain in the soil, the cesium, for example, they will add the equivalent of 3 weeks to the average lifetime exposure to natural background. These natural variations mean, for example, that by moving from, say, Hampshire to Cornwall, you could double your annual radiation dose. And it has been said that the increased public exposure, occasioned by all the leaks from Sellafield, amount to spending perhaps 2 or 3 weeks in the vicinity of Aberdeen. One of the effects of the increasing concern about radioactivity has been the development of more and more accurate ways of measuring radiation, and that in some cases has led to greater concern. Because as the scientists have continued to explore both the sources of radiation and its effects, they've come up with 1 or 2 surprising results. One of them, for example, is the hazard represented by the naturally occurring radioactive gas called radon that collects in our houses. This old Victorian stone house in Cornwall was taken over some 18 months ago by the National Radiological Protection Board, the NRPB, as part of a study into ways of reducing the build-up of radon gas in houses. They measured levels in 2,000 houses, and the results indicate that across the country, in as many as 100,000 homes, people are getting the same sort of exposure as allowed to nuclear power station workers. And in many homes, perhaps as many as 1,000, they're getting 5 to 10 times the exposure of nuclear power station workers. And that's one of the reasons why radon gas has become a major focus of international concern. Because for most of us, radon gas is now the biggest single source of radiation exposure, apart from the occasional X-ray. And paradoxically, the situation is made far worse by the modern passion for double glazing and draft proofing. In a well-ventilated, that is to say, a normally drafty house, most of the radon gas leaks away. But where it's trapped, by double glazed windows, for example, or sealed doors, it decays into other substances known as radon daughters. They're particles, they can get trapped in the lung, and they can cause lung cancer. Indeed, it's shown they can cause as many as 5 to 10% of all lung cancers. And we can demonstrate how that works. What we've got here is an alpha counter because radon and radon daughters give off alpha radiation, the kind that's most damaging to human tissue, and a kind of mechanical lung, sucking the air in the house through a white paper filter, which is acting rather like your bronchial tubes, collecting particles of radon daughters. Now, if I expose the alpha counter to the air in the house, there's no reaction because the concentration of radon daughters is too low. If I now test the filter, i.e. your bronchial tubes, you can hear there how many particles are collected in just half an hour, the time we've been running the mechanical lung. Now, compared with radon gas, most other sources of natural background radiation really pale into insignificance. But there are some. For example, even the food we eat can be radioactive. Brazil nuts are rich in fats and protein and good for us in all sorts of ways. But they're also mildly radioactive. They contain radium and thorium, both alpha emitters. Many mineral waters have higher than average concentrations of radon gas, again an alpha emitter. One of the vital elements we all absorb from our food is potassium, but one form of potassium, K40, is also radioactive. We all carry some K40 in our bodies all our lifetimes, bombarding us from the inside with 200 or 300 particles a minute. Now, why am I going on about this? Why am I going on about radioactivity in our houses, radioactivity in our food and so on? Well, certainly not to alarm you, but there are 2 or 3 important points to be made. One is that scientists agree that nature is the biggest source of radiation for all of us. Concorde pilots, for example, are essentially radiation workers. They carry exposure meters on their lapels because of the higher than average doses of cosmic radiation they receive during their high-level flights. The second point is there is no real difference between all these sources of radiation: nuclear power station emissions, medical X-rays, and the radioactivity in our food and so on. They're all the same. But most important of all, if the cells in our bodies were to shrivel up and die when they were hit by, say, a beta particle or a gamma ray, there wouldn't be many of us left around. The fact of the matter is that because we have evolved on a radioactive planet, we've developed repair mechanisms that can make good most or all of the damage we incur from the radioactivity in our food or the radon gas in our houses. Now, the problem is that most of us misunderstand the hazards of radiation. Very difficult for us to separate out the harmless from the worrying. When, for example, we asked a sample of the British public a few weeks ago about their understanding of the hazards of radiation, one of the questions we asked was, how near can you safely be to the following substances?
A piece of granite.
Could touch it.
A lump of uranium ore.
Could not touch.
About an ounce of plutonium.
You could not touch.
But could you be in the same room as it, do you think?
No.
A fuel rod before it goes into a nuclear reactor.
Could touch.
The fuel rod after it's been used in a power station. I suppose you could really be in the same room as that, but not touch it.
In that survey were listed 5 items: a piece of granite, a piece of uranium ore, an unused fuel rod, a piece of plutonium, sometimes called the most dangerous material on Earth, and a used fuel rod. We asked people to choose whether they could touch the substance, be in the same room as it, or whether they would have to be behind some sort of protective shielding. Let's look at the results we got for the first material, granite. 88% of the people questioned, that's roughly 9 out of 10, saw no problem with holding granite. They were right, although there were 1 or 2 doubters. The official answer, well, that has them all in the same room holding the granite. Well, as you might expect, most people saw no problem with granite, although 12% thought you had to take some care. It is, of course, one of the commonest rocks in these islands, the Scottish Highlands, Dartmoor and all that. It is lightly radioactive. I can, for example, get a reading on this Geiger counter. There you can hear the radioactive emissions, and it is involved in the creation of radon gas, so a slight radioactive problem with granite. Let's move on now to uranium ore. 22% of the people questioned thought that you could safely hold uranium in the hand. A further 22% saw no problem about being in the same room as the stuff, but 49% saw a need for some sort of protection from it. In fact, the official answer is that you're not likely to come to any harm holding uranium. This, of course, is what a lot of the fuss is about, the basic raw material of the nuclear power industry. Much more radioactive, of course, than granite. You can hear there the fierceness of the Geiger counter's response, but still quite safe to handle, otherwise I wouldn't be handling it. Now, the uranium metal is refined from the ore and goes to make up the fuel rods that go into many of Britain's nuclear reactors. How close can you get to those? Well, almost 2 out of 10 people believe that you could hang on to them. Another 2 saw no problem in being in the same room, but most people, 56% in fact, only felt happy with a wall between them and the uranium fuel rod. The official answer, surprise, surprise, is that you can safely hold these rods. So over half the people surveyed thought you couldn't get near one of these. In fact, as you see, you can. Although, let me emphasise, it is an unused fuel rod, hasn't been anywhere near a reactor core. Something like 50,000 of these would go to make up a typical reactor core. In some ways, safer to handle than the uranium ore itself because it's encased in this magnesium alloy cladding, what they call a fuel can. OK, that's a fuel rod. Let's move on now to the element plutonium. Plutonium is a word inextricably bound up with the bomb, so understandably perhaps only 16% thought you could safely be anywhere near the material. Almost 8 out of 10 people wanted to have nothing to do with it. The official answer, to most people's surprise, is that you can safely, if not happily, be in the same room. Well, we've got some plutonium inside this double-skinned plastic bag. Plutonium has really had a very bad press down the years. It's been variously described as the most deadly or the most toxic substance on Earth. But if toxic means poisonous, there are many other chemicals far more poisonous than plutonium, things like arsenic and cyanide and so on. It's also thought to be such a powerful emitter of radiation, you have to stand a long way away from it. Well, that obviously isn't the case, otherwise I wouldn't be as close as this to it. But let's not minimise the dangers of plutonium. Its real dangers lie in the fact that it's a powerful emitter of alpha radiation that can be contained safely by this double-skinned plastic bag. But if a particle were to lodge in the lungs, then the heavy alpha particles could cause a great deal of damage. It's also active for a very long time indeed, well over 200,000 years. So it goes on causing damage for that sort of period of time. It's the stuff of bombs and weapons, of course. So every milligram of plutonium has its own docket. It has to be accounted for wherever it goes. So that's plutonium, not quite perhaps as fearsome a material as its reputation would have us believe. But what about the last of the items on our list, the used fuel rod? Well, that's 20 feet down at the bottom of this cooling pond. As for the general public's response to the idea of being adjacent to one of them, well, almost 9 out of 10 people wanted to be behind some form of protection. And indeed, the official answer in this case is to stay well away, because used fuel rods are perhaps the most potent concentration of radioactive materials on Earth.
A fuel rod might stay inside a reactor for anything up to 10 or a dozen years, and by the time it comes out, it's so hot and intensely radioactive that to get anywhere near it would mean a lethal dose of radiation. Indeed, it has to be kept at the bottom of a pond like this for 3 or 4 months before it's safe enough even to transport in a container for reprocessing. It's giving off 1 million times the annual recommended dose for a member of the general public. And it contains materials that have really to be kept away from living matter virtually until the end of time.
But the fuel rods apart, as far as most of these materials are concerned, it looks as if the public fears of radiation have become, in some cases, somewhat exaggerated. So how have the terms radiation and radioactivity, at whatever level they're experienced, come to acquire so universally a bad reputation? Well, most of us get our information from the media. So we asked Jennifer Brown to examine the way in which the media handles this particular subject. And our first observation was that this torrent of condemnation presently hurled at the nuclear power industry is a relatively recent phenomenon.
If you look at newsreel pictures of 20, 30 years ago, and you look at the pictures now, I think the most remarkable thing is this enormous change of tone from a rather jolly, almost jokey commentary to the rather serious, much more considered view now.
Mary Munro III puts to sea under skipper Alec Mellon to fish for strange fish. She's looking for traces of atomic energy. It may be in the air, so they collect samples with a good old vac. They're checking to see whether waste matter discharged to sea from Windscale Atomic Factory makes the seawater dangerous. Before discharge from the factory, the waste is carefully treated to make it safe. Yet, as an extra safeguard, samples of water and mud are taken for laboratory tests, which have so far proved negative. There's no danger of an atomic kipper. They even test the fish.
Cumbria's remote coastline was chosen as the ideal site for Britain's first atomic bomb factory. That was back in 1947. Today, Windscale's reprocessing operations are exposing people living near the coast to radioactive pollution. They can't avoid it. When the contaminated estuary mud dries out, radioactive dust particles can be measured, blowing in the air.
In a steel sphere 20 stories high, America's first atomic electricity for commercial use is ready to flow along the grid to homes and factories in New York State. This atom-powered steam generator produces enough current for a city of 30,000 people. And at the first house along the line, they're cooking with atom juice already. Nuclear hamburgers coming up.
The 3 Mile Island nuclear plant near Middletown, Pennsylvania. 12 days ago, the reactor ran out of control, spilling dangerous radioactive waste into the atmosphere and came close to catastrophe. The implications of the accident are far-reaching. American nuclear salesmen have sold reactors like this to many countries, including France and Germany, and they're hunting for new orders in Britain. Tonight, World in Action reports from America and Britain on the future for nuclear power in the aftermath of a nuclear nightmare.
And I would put down that change of tone to a number of factors. One, and I think a principal one, is the loss of confidence in expertise. Experts have been found to disagree, wrong, there have been misdoings, certainly the recent shuttle disaster, suggestions that in fact there's been collusion and fraud. And so people are now, I think, much more suspicious and suspect of expertise. Disputes take place in public. People are confused about alternative views, so there is no authoritative source.
There is no doubt that the major proportion of media comment on nuclear power these days is highly critical. The tone varies from newspaper to newspaper and from programme to programme, but the vast bulk of it is anti. In fact, we take it for granted that it will be.
It was a Sunday paper where they showed the cloud over London that might result from.
Jennifer Brown and her colleagues have been looking at the ways in which different journalists use what they call their primary sources, which are in effect simply press releases and handouts from the main interested parties.
And when you look at those primary sources, you find that there are two dominant images from the nuclear industry. One is a high-tech, patriotic, nuclear power is good for Britain, and the other is a sort of pastoral idyll which says that nuclear power is essentially something which is harmonious with the environment, that it doesn't do it any harm, that it sits in fields with animals grazing happily around it. The environmental lobby will actually do a rather different thing. They will say that nuclear energy is prejudicial to the well-being of the environment and ultimately to the people of this country and, in fact, the world. And they will promote a much darker image of the negative side of nuclear energy. What happens with respect to the newspapers and television is that they use those primary sources and they tend to accentuate them. They lean towards the negative images and they caricature the positive images coming from the nuclear industry. So one gets pictures of skeletal sheep, two-headed sheep, which are in a sense making a joke and a negative point. What happens in the newspapers is you get headlines, say, of the Chernobyl disaster and little pictures of mushroom clouds. Or you get cartoons where you have, again, power stations alongside rockets, so that the newspapers tend to pick up on and put together the military and the civil, which is to get the images from the environmental sources. All the best jokes go with the anti-nuclear lobby. The mismanagement, accidents make much better stories than the nuclear power station work perfectly well today. If there is mismanagement and accidents, then I think it's absolutely right that the newspapers highlight it. But the complaint is that, in fact, the nuclear industry is that the media jump the gun. They either promote what-if disaster stories, or they present it in such a way that it does over-dramatise and actually make claims that the nuclear industry would say we're totally unrealistic. Of course, the anti-nuclear lobby would say that's about the right emphasis. But what we essentially have here is a clash of values and a clash of interpretation. It's very difficult to say whether one is right or accurate, but we just have different interpretations of the evidence, and the media tends to pick up on and accentuate the dramas, the mishandling, the mishap. And in a sense, I think they think that the nuclear industry is on the run, and it's a good story.
But as we saw earlier, the good stories about radiation and radioactivity haven't always been the critical or the anti-ones. In fact, the history of this topic has seen a regular alternation of the near-miraculous and the calamitous, as each new step in the understanding of the science of radiation has brought with it a new understanding of the hazards. And the public first learned about all this with the extraordinary invention of X-rays.
Late in 1895, in a little university laboratory in Bavaria, Professor Wilhelm Conrad Röntgen first noticed the strange effect which led to the announcement of his discovery of X-rays. And although the news was received by the public with a mixture of disbelief and apprehension, doctors immediately saw the possibilities of the mysterious new rays and began to use them. It was not until
In the early days, the newly discovered radiation was an exciting novelty, with little hint of the harm it might cause. Thomas Edison demonstrated X-rays at an exhibition in New York in 1896 and helped to make them a media miracle. Edison seems unaware of any danger as he stands bathed in the light from the X-ray lamp, although he was soon to discover that this technology wasn't entirely safe. His assistant, Clarence Daly, whose hands were often used to demonstrate the penetrating power of X-rays, was one of the earliest people to die from a radiation-induced tumour. The rays cause cancer by damaging individual body cells, like these human white blood cells that have been subjected to very high doses of radiation. Where a normal cell will progress smoothly towards a division, the irradiated ones show severe problems as they grow blobs on their surface. Within the cells, radiation can affect the chromosomes that contain the vital genetic code, and high doses can cause major deformities and breakages. The result is that the normal mechanisms of growth and reproduction no longer work properly, and the damaged chromosomes might cause the cell to die or become a cancer cell. For many years, these effects weren't really understood as scientists continued to experiment. Despite this lack of knowledge, X-rays were offered as treatments for all sorts of major and minor problems. Devices were advertised to doctors to help children with ringworm, for example. The X-rays would make the child's hair fall out and reveal the site of the infection for it to be treated with ointment. No one knows how many of these children developed cancer in later years as a result of this sort of treatment. In fact, cancer itself, in this case cancer of the cervix, was seen as a focus of X-ray treatment, since very high doses could kill off malignant cells. And faced with a tumour like this, who could fail to marvel at this transformation after X-rays? At the same time as the discovery of X-rays, scientists like Marie Curie were conducting experiments with another type of radiation, and the first radioactive materials were being investigated in the laboratory. The most well-known was the element Marie herself discovered, radium. In the light of what we now know, drinking and bathing in radioactive water seems inexcusably reckless. And the benefits of a radioactive corset are hard now to appreciate. But there seemed to be no limit in those days to the variety of products which use radioactive materials. Some of them have since been collected by the National Radiological Protection Board in a sort of mini-museum of radiation horrors.
Dr. Morrow, what exactly have we got in these cases?
A series of objects which contain radium and which date from the early part of this century. And although this is a collection that has been gathered together in the United Kingdom, you could have had a similar collection in any other country. For instance, you have the sparklet siphon bulbs at this side here, and those will be used for a sparklet siphon, and instead of having scotch on the rocks or scotch and soda, you'd be drinking scotch and radioactivity.
What's that object in the corner there called an emanator?
Well, that produces radon gas, and radon is the daughter product of radium. When it decays, it forms radon gas. And that little object produces radon, and you can either breathe it, inhale it, or else you could filter it through into the bath water and have a radium bath, as they called them. And one of those was advertised in the early years of this century, and they were told that, or the customers were told, that it would be quite convenient because you could have your radium bath at home.
What about this radioactive blanket?
Well, this is a rather bizarre way of treating rheumatism. Somebody had the idea that not only could you do this by heat with a normal electric blanket, but you could also use the gamma rays of radium, and hence they impregnated this blanket.
One aspect of radioactive substances that excited many people was that they could cause all sorts of things to glow in the dark. From fishing floats to buttons, radioactive luminous paint was applied to countless articles. Unfortunately, the ladies who applied the paint often used to lick their brushes and received doses of radiation that led years later to the development of facial cancers. Indeed, Marie Curie herself was to become one of the martyrs of radiation. She died of leukemia, caused by the substances she experimented with. But the growing awareness of the dangers wasn't enough to stop the scientific research. Indeed, the first 2 or 3 decades of this century was a period of immense scientific excitement as discovery followed discovery. Many of them were made in the UK by one of the greatest pioneers in the field, Ernest Rutherford. The next important steps in the story took place in the 1930s here in the Cavendish laboratories in Cambridge. Rutherford was appointed professor here in 1919, and he became a sort of legendary figure as he gathered around him a group of young men who were to become among the leading physicists of their generation. Now, we can get some idea of what it was like to work around Rutherford, strangely enough, from that crocodile carved on the wall behind me. It was carved by a Russian professorial colleague of Rutherford's called Peter Kapitsa, and in Russian folklore, apparently, the crocodile stands for power and terror, and Rutherford must have inspired a great deal of both in colleagues and students alike.
In our laboratories today, we live in an atmosphere dim with the flying fragments of exploding atoms. And on this occasion, I wish to say a few words on the methods and ideas employed to break up atoms and to realize, if even on a small scale, the old dream of the alchemists of transmutation of one element into another.
Rutherford and his colleagues probed the structure of the atom over 30 years of detailed experiments. One of his biggest contributions to physics was the nuclear theory of the atom, the idea that the atom had a tiny but very heavy nucleus, and his notebooks showed the first sketches of this idea. But how on earth could the atom be investigated? How could an invisible and intangible speck of matter be made to yield its secrets? Well, by firing particles they couldn't see at atoms that were themselves invisible, they discovered that there was a nucleus and that it had an electrical charge. Now, they deduced this from the fact that the majority of particles fired at the atom were only slightly deflected. However, a few that headed straight for the nucleus were very strongly repelled. It was, said Rutherford, as if a 15-inch shell had been fired at a sheet of tissue paper and rebounded. So there was obviously something very special about the nucleus of the atom. In fact, it wasn't just a hard ball either. And what's more, it seemed to change the very nature of particles fired into it. News of these experiments soon spread, and an army of scientists throughout Europe tried to make sense of them. Underlying the actual experiments were some of the radical new ideas being generated by the theoretical physicists. One of them gave an early hint of the kind of power that might be locked up in the atom. It came from Albert Einstein.
It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind.
This simple-looking equation has always frightened people off. What it says is that any mass m has the potential to be converted into energy, E. In fact, into an immense amount of energy. Now, to find out just how much energy you could get out of 1 unit of mass, you must multiply it by a very large number indeed, c, which is the speed of light squared. It means that 1 unit of mass, the particle on the left, can be turned into a vast number of units of energy on the right. In fact, a 1 with 21 noughts after it. If only, that is, someone could find the way to make the transformation from mass into energy. But such practical aims were a long way from the thoughts of the scientists working under Rutherford at the Cavendish. They concentrated on the task of understanding the inner secrets of the atom. In various rooms around the Cavendish, people like John Cockcroft and Ernest Walton produced bits of apparatus that today wouldn't look out of place in a junk shop, most of them for pennies rather than pounds. Indeed, the most expensive piece of apparatus here was said to be the famous Cockcroft-Walton accelerator. Cost around £500, was used to accelerate nuclear particles called protons, and then shielded by the very latest in radiation protection gear at the time, a sort of lead-lined tea chest. They fired the protons at atoms until they achieved what was then an immense goal. Today is something taken for granted by every schoolboy, the splitting of the atom. it was still pure knowledge they were pursuing, as their experiments told them more about the particles that made up the nucleus. So although the work carried out here in the 30s was very much a stepping stone towards the harnessing of nuclear power, no one here realised it at the time. Even Rutherford, for example, said in 1933, perhaps prompted by the enormous electricity bill run up by the Cockcroft-Walton accelerator, that anyone who looks for a source of power in the transformation of atoms was talking moonshine. And it wasn't really until early 1939 when two famous papers were published in the scientific journals reporting the first verified experiments on nuclear fission that it was realised that the powerful forces locking the nucleus together could be released. So Rutherford was proved to be wrong. There was an immense source of power in the atom. The key discovery of this period was nuclear fission. The fact that if you fired a neutron as an atom of uranium, the atom would sometimes split in a very dramatic way. When the split happened, the atom gave off 3 more neutrons and a burst of energy, gamma radiation. But since it was neutrons that started the splitting, if there were other uranium atoms around, one or more of the extra neutrons given off could now cause them to split. You would get a chain reaction. Now, if more than one of the neutrons from each fission split other atoms, the chain reaction would accelerate, releasing more energy and more neutrons each time. If the conditions were right, this chain reaction could trigger off an immense explosion. The implications of these pieces of pure science assumed a new significance with the outbreak of the Second World War. The chain reaction could form the basis of a bomb more powerful than any other. British scientists were asked to advise the government on the design of such a super bomb. Among them was Rudolf Piles.
It had been taken for granted that you could not make a weapon with natural uranium, and that indeed is true. But what we suddenly realized was that if you could separate the uranium isotopes and pull out the very rare isotope 235, then a reasonably small quantity of that could make a very effective weapon. And while isotope separation was something very difficult, which had been achieved only in minute quantities in the laboratory, it seemed worthwhile to do it for this result.
Meanwhile, the British government was losing interest in the whole idea of such a super bomb in the face of the more immediate Nazi threat. However, the scientists continued with their researches, and in the summer of 1941, a select steering group, known as the Maud Committee, presented a report on the uses of uranium for a bomb. This report was sent to America, together with a number of leading British nuclear scientists. A grant of $2 billion was made by a Congress that wasn't told it was to be spent on the ultra-high secret Manhattan Project. The world only learned of the scientists' success on August the 6th, 1945. So in the space of just 5 years, the theory of how to initiate a fast nuclear chain reaction had been converted into a massive and permanent fact. What the scientists had achieved is what's called a prompt criticality, a process which, once initiated, once it's been lit, so to speak, can no longer be controlled. In fact, prompt seems altogether too blunt, too clumsy a word to describe what goes on in the bomb, because the violently expanding sphere of atoms, each one splitting and releasing more neutrons, reaches temperatures of 1,000 million degrees in just 1/10 of a second. But there was another option, largely ignored in the excitement of the war effort, because the Maud report had a second section which discussed the feasibility of a uranium boiler to generate electricity. Turn the pages back a little earlier, in fact, to the turn of the century, and there were one or two visionaries around, writers and scientists, who had imagined the world transformed by the energy of the atom. One of them was a man called Frederick Soddy, who wrote in 1903 the following words: "If the energy in the atom could be tapped and controlled, what an agent it would be in shaping the world's destiny. A man who put his hand on the lever by which nature regulates his energy would possess a weapon with which he could destroy the earth if he chose. And the nation, which can transmute matter, could transform a desert continent, thaw the frozen poles, and make the whole world one smiling Garden of Eden. Well, the weapon that could destroy the earth had been amply demonstrated. But what about this attempt to control that power, to achieve an altogether slower chain reaction? Well, the quest for that nuclear Garden of Eden began with great optimism in the late 1940s. In next week's programme, we explore what has happened to it since.
This is an old, disused mine in Cornwall. They used to mine copper here, but in these rocks there are clear indications that we live on a radioactive planet, and indeed always have done. When the Earth was cooling all those millions of years ago, a few of the elements that make up the rocks of this planet came to have atoms with the unusual quality of splitting spontaneously, what we now call radioactivity. One of them is uranium, and in these rocks there are seams of uranite or uranium ore. You can hear some of the radioactivity being given off by these small deposits. What's happening at the atomic level is that the nucleus of the uranium atom releases a cluster of particles and a burst of gamma radiation. It's a phenomenon that, as I said, has been going on since the beginning of time on this planet. But only in the past 3 or 4 decades have we attempted to harness it in the form of nuclear power. However, 2,000 million years ago, on a part of the planet that we now call Africa, it seems that nature constructed the world's very first nuclear reactor. Imagine a broad, muddy delta on the shores of some primeval sea. Over many thousands of years, the rains and the weathering leached the uranium from the rocks and the mountains and carried it down to swamps that lay along the river banks. Here, primitive forms of life reduced it to an insoluble form, so that it was laid down in the layers of silt and mud. As the centuries passed, the weight of sediments above compressed the uranium-bearing layer into a critical mass. All that was needed to complete the process was the folding and the cracking of the sedimentary layers to allow water to filter through to surround this natural reactor core with what is known as a moderator. Eventually, the reactor started up, and it's estimated that it ran for 750,000 years. Now, the remains of this reactor were only discovered a handful of years ago, but by then, of course, this extraordinary physical accident of fission had come to dominate this planet in all sorts of ways. It gave us our most potent symbol of destruction, and it was hailed as the great new source of cheap power.
Britain's first atomic power station. peaceful revolution succeed another with astonishing speed. But we who are close to it can hardly realize that so short a period encompassed the invention of the motor car, the wireless set, the aeroplane, and much else besides, which we now take for granted. It may well prove to have been among the greatest of our contributions to human welfare that we led the way in demonstrating the peaceful uses of this new source of power.
Of course, Calder Hall was billed as the world's first nuclear power station. Nothing was said in any of the publicity, and they probably didn't even mention to Her Majesty the Queen that the primary purpose of Calder Hall was to manufacture more nuclear weapons plutonium, and that the electricity was a byproduct.
It was said at the time that this electricity would be too cheap to meter, and it was welcomed as one of the greatest gifts science had ever made to mankind. But no mention was made in all of this of the fact that nuclear power inevitably involved handling dangerous radioactive materials. And just what kind of threat radiation posed, we were just beginning to learn from the after effects of the bomb. The immense, awesome, destructive power of an accelerating chain reaction had been predicted theoretically and then demonstrated practically in the Nevada desert in the early months of 1945. But the first human exposure to this terrible power took place on the 6th of August of that year. The effect was a vast devastation as far as the eye could see. A single bomber, a single bomb, and entire cities were laid to waste. Hundreds of thousands of people were killed and injured. The power of the atomic bomb to destroy and kill and maim may have stunned the world, but it came as no surprise to the scientists who had helped to fashion it.
We pointed out that there would be radiation effects, and that for that reason, and also because of the range of the destruction, there were probably not many uses of the bomb which would not kill very many civilians. We said this might make this weapon unsuitable for use by this country.
But at the time, who could have stayed the hand of the generals? The Allies were under immense pressure to bring the war to an end. And faced with destructive power on this scale, the Japanese capitulated within days. It's 40 years since those bombs were dropped, and the cities have long since risen from the rubble to continue their lives. But even at this distance, it's impossible to approach this subject without a profound emotional response. And that, of course, is the albatross that hangs around the neck of the nuclear power industry. The scientists are still wrangling about how much radiation was released and what its effects have been. And the focus of their attention is not so much the people who died, but the 300,000 or so people who were further away from the centre of the explosion, but who received large doses of radiation. These survivors have been a major focus of scientific attention ever since, the world's largest study group on the effects of radiation. By following them over the remainder of their lives, the scientists can compare their patterns of illness and causes of death with a similar population who have not been exposed to these high doses of radiation. Now, of the 280,000 survivors, some 80,000 have been carefully observed over the years since 1945. Around 24,000 of those people have since died from a wide range of causes. When we look at cancer deaths, however, it turns out to have been the cause of death for only 5,000 people. Of course, in any population group of this size, not exposed to the bomb, there would in any case be a large number of deaths from cancer. The question is, how many extra cancer deaths occurred that might be attributed to the effects of the bomb? The results suggest, somewhat surprisingly, that among the survivors of the bomb, there were only some 250 more cancer deaths than would have occurred in a similar population not exposed to these very high doses of radiation. 250 deaths amounts to roughly 5% of the cases of cancer. But what about genetic deformities? During the 9 months after the bombs, there was a major increase in the two cities in the number of children born with deformities, due obviously to the high doses of radiation received while they were in the womb. But there was another widespread fear. Might the children of the bomb, when they grew up, themselves give birth to deformed children? Only now, after a whole new generation of Japanese children have grown to maturity, can an answer be attempted to the question of whether or not, for example, the damage suffered by this little girl in the womb will be passed on to her descendants. Well, as far as science can tell, the damaging effects of radiation are not carried over to succeeding generations.
So that's our understanding of the effects of the bombs at Hiroshima and Nagasaki, viewed as it were through the long telescope of time after 40 years of evaluation and re-evaluation. But back in 1945, there was a remarkable ambiguity in the Western response to the bombs. There was, of course, immense pride at having fashioned a weapon that had smashed the Japanese war machine, but mingled with immense horror and disbelief at the sheer scale of the death and destruction. But at the centre of it all, there was an extraordinary hope, a belief that the scientists had somehow fashioned a magic key that could unlock a bottomless treasure chest of cheap energy. And before long, it wasn't just the public, but the scientists and engineers who were being swept along on a tide of pro-nuclear euphoria.
In fact, that tide of euphoria had been gathering pace for 2 or 3 years. Indeed, in 1940, within months of the revelation of the first experiments on nuclear fission, one scientist had cobbled together his vision of a brave new atomic world. People would live in spacious underground apartments with rooms and swimming pools heated by private nuclear reactors. Cars and buses would run on nuclear engines, and huge supersonic airliners would be powered by streams of radioactive particles and be able to cross the Atlantic between lunch and dinner. And even then, he envisaged a terrifying weapon that could destroy the world.
Before dawn on the 16th of July, 1945, at Alamogordo, New Mexico, an event took place which was to change the world for all time to come.
But the tide of propaganda gathered pace throughout the 40s and 50s in an attempt to blot out the memory of the bomb and persuade the American people that the atom was a force for good. It was hailed as the answer to a dream as old as man himself, a giant of limitless power, power to light homes and cities across the American homeland.
The atomic energy power plant has already proved feasible. The future supplying of electric power to entire cities is far from impossible, while nuclear power in locomotives, submarines, ships, and even very large airplanes may all but revolutionize future transportation on land, sea, and air.
But over the first 30 years or so of the atomic age, few of those dreams have been realised. The nearest the world got to an atomic airliner was the testing of a small reactor carried inside the fuselage of a bomber. No one could solve the safety problems. It would lay down, for example, a trail of radioactive waste, and what would happen to the reactor if the plane crashed. As for the passengers, well, they would probably have to be banished to the wingtips to protect them from the radiation. A nuclear ship did actually get launched. It was unquestionably the world's most expensive merchant ship. It cost $30 million and took 5 years to design and construct. It was called the Savannah. The dock workers around the world refused to handle what they described as a floating atomic bomb. As for the atomic car, well, the Ford Motor Company toyed with the idea of a model neatly labelled the Nucleon, but very rapidly this project died a death. However, these practical setbacks scarcely stemmed the flow of pro-nuclear ballyhoo.
Truly, the superpower which man has released from within the atom's heart is not one, but many giants. One is the warrior, another is the engineer, another is the farmer, still another is the healer, and the last is the research worker working in the fields of pure science to reveal more of the mysteries of the universe. But all are within man's power, subject to his command. On man's wisdom, on his firmness in the use of that power, depends now the future of his children and his children's children in the new world of the atomic age.
The tide of near euphoria that swept across America had become a sort of muted enthusiasm by the time it reached our shores. And that's not just because of the famous British stiff upper lip. The American Congress had slammed the door in the face of the British scientific establishment. They'd passed the notorious McMahon Act. And in accordance with this act, it was forbidden to pass the results of nuclear research across to the UK, even if British scientists had worked on that research, as they had, of course, on the Manhattan Project developing the atom bombs. Even today, the McMahon Act is spoken of in this country with great bitterness. But the result, of course, was to launch Britain into its own nuclear research programme. And Harwell was set up in the late 40s and became a sort of symbol of Britain's nuclear prowess. Britain was still going through its love affair with the scientists that had developed during the war years. Then they had invented the weapons that had led on to victory. Now they were shaping Britain's nuclear future. Up until the mid-50s, the nuclear emphasis in the UK had been almost entirely upon weapons production. But even in the late 40s, scientists at Harwell were working on the problems posed by a civilian nuclear power programme. They thought in terms of a dual-purpose reactor, neatly labelled PIPA, which stands for pressurised pile, producing both plutonium and power. And many of the suspicions today about the mingling and merging of both the civilian and the military programmes stem from this time when, of course, they were working hand in hand. Now, the PIPA programme became the first reactor at Calder Hall. It does indeed produce both plutonium and put some power into the grid. The power was, of course, a secondary function. Calder Hall's main task was, and still is, to produce weapons-grade plutonium. But at the time, the CGB was by no means convinced it wanted anything to do with nuclear power. But all the forecasts predicted a massive growth in the country's electricity needs. British homes had been taken over by the American passion for domestic appliances. Industrial demand was expected to zoom, and the lights were going on in towns and cities up and down the land. It all added up to a huge programme of power station building in the 60s and 70s. And nuclear power was seen as a vital part of the mix. In 1955, the Minister of Power announced a programme for 3 or 4 nuclear power stations. 2 years later, the order was increased to 9, possibly 12 stations. The point was made then, that is so often made today, that from the turbine hall in the power station all the way up to the end user of the electricity, the technology is the same, whatever fuel is used to generate the heat. Today, in 4 out of 5 power stations in the UK, that fuel is a hydrocarbon, coal or gas or oil. In just 15, the fuel is uranium. And although nuclear engineers talk of a burn-up, there's no fire in any conventional sense. The heat in a nuclear power station is produced by triggering off and then sustaining a continuous, controlled, slow chain reaction. As the atoms of uranium are split, they release neutrons and a burst of gamma radiation. The neutrons collide with other atoms of uranium-235 to ensure that the chain reaction is kept going. The uranium fuel is made up in several different forms, but in the first generation of British nuclear power stations, the uranium comes in the form of solid metal rods, about 1 metre in length, which are encased in magnesium alloy containers, or cans as they're called. Then they're stacked, one above the other, in channels cut through a massive graphite block that makes up the core. Now, the graphite block is in fact made up of interlocking bricks of graphite, and it serves as the moderator. The role of the moderator is to slow down the neutrons that are flying around in the core so that they score more hits on the uranium-235 atoms and therefore keep the reaction going. Now you need some device, some switch for turning the reactor on. For that, they've got what they call control rods, made of a boron steel which has an immense appetite for any free neutrons that are around. So while they're inserted in the core, they mop up the neutrons that are flying around, rather like a sponge mops up water, and stop the reaction from starting. As they're slowly drawn out, so more and more of the neutrons score hits on the uranium-235 atoms, and the reaction gets underway. It goes critical, to use the jargon. That phrase, by the way, has no connotation of danger or absence of control in the core. It simply means switching it on. The whole thing is encased in a 3-inch steel pressure vessel, and that is housed in several metres of concrete to keep in the radiation, the neutrons that are flying around, and gamma radiation, stop them escaping into the environment. So the control rods are drawn out, the reaction gets underway, immense heat builds up in the core. You need some device now to get that heat away from the core where it's useless to where it can do some work in converting water to steam to drive the turbines. For that you have what the industry calls a coolant. In the very earliest British reactors, the coolant was simply air. And it's somewhat chilling to recall, in the light of what happened at Chernobyl, that they had open-ended systems. All they wanted was the plutonium. The heat created in the process was an embarrassment. So air was simply sucked in at the bottom, blown through the reactor core by immense fans, and then vented out of the chimney into the environment.
As it happens, one of Britain's earliest and greatest nuclear pioneers, Sir John Cockcroft, was rather unhappy with this arrangement being carried over into the Windscale reactors which were being built at the time. So, somewhat against the advice of his colleagues, he arranged for immense filters to be fitted into the chimneys at Windscale. They became known as Cockcroft's Follies. In the light of what happened subsequently, that was a very important piece of foresight.
On the 8th of October in 1957, a technician operating the Windscale No. 1 plutonium production pile threw a switch too soon. He didn't realize he'd done anything wrong or that anything had happened. It wasn't for some hours that they began to detect radioactivity escaping from the tall stack that is one of the characteristic features of the Windscale site. And eventually, when they investigated, they realized that the reactor was on fire, that there was what eventually came to be 11 tons of uranium, plus the graphite surrounding it, on fire inside the core.
They tried to control it by isolating, shutting down, doing whatever was necessary. And in the end, they had to take the decision to put water on it. That's quite a brave decision to take, putting cold water onto hot or burning metal, because you may get some sort of steam explosion or chemical reaction, which is what happened at Chernobyl.
Eventually, what they did was they evacuated the site, and 3 senior people were left in the building. They attached fire hoses to the channels above the part of the reactor where the fire was and turned on the fire hoses. And they didn't know whether, in fact, when putting water onto a blazing metal like that mightn't produce a massive explosion, which would have blown the reactor apart and discharged radioactivity all over the landscape. But they got away with it. They managed to put it out. And they then released statements saying that the wind had been blowing out to sea, so no radioactivity had gotten to the British public. What they didn't reveal was that the radioactivity had not only gone right across Britain, but right across northern Europe, as was subsequently detected.
Emergency at Windscale Atom Plant, and the milk from 200 square miles of farmland is condemned as radioactive. But for these filter tops, once nicknamed Cockcroft's Folly because Sir John Cockcroft insisted on them, farms much farther away would have faced not emergency but disaster. Milk marketing board lorries collect the contaminated milk. The trouble arose when radioactive dust from the overheated pile fell on the Cumberland pastures, and milk samples rushed to Harwell were found to contain 6 times as much radioactive iodine as international health standards permit.
So the Windscale fire marked a watershed in the public perception of nuclear power and indeed of the nuclear scientist.
People at large, I think, realised that you could have accidents even with this marvellous nuclear power, which was going to give us all free electricity at one time. The government reacted in the usual way to a big emergency, a big disaster like that. And they set up an inquiry. Sir Alexander Fleck conducted an inquiry and made a report.
The Windscale report led to the establishment of a body to oversee the way nuclear power stations were built and run, the Nuclear Installations Inspectorate. It also led to a much more active research programme into the effects of radiation on human health.
We have a lot of information about the delayed effects of radiation on man from the experience of man. It starts off with the experience of the early radiologists who had exposure to radiation levels far above those which we would allow today. It goes through the use of radiation in the treatment of diseases where we think today the risks are too great.
Now, a good example of that is X-rays, because X-rays are similar to other types of radiation. So they became a valuable source of information about the kinds of effects that might be associated with lower doses of radiation from whatever source. Now, between 1935 and 1954, 13,000 patients with a crippling back complaint called ankylosing spondylitis were treated with X-rays. But when those same patients were studied years later, it was found that some of them had developed a variety of cancers as a result of the treatment. So this was further evidence of the cancer-causing effects of radiation. And even lower doses of X-rays, the sort of levels that were used to examine pregnant women, were later shown to have a significant risk attached to them. By following up the children of several thousand women who'd been X-rayed in pregnancy, it was found that the radiation led to an increased risk of leukemia in the children in later years, particularly if the mother had been X-rayed during the first 3 months of her pregnancy. and normally 2 in 1,000 children might be expected to develop leukemia. In the case of children who've been x-rayed in the womb, however, it rose to 3 cases in 1,000. And those discoveries led eventually to a general reduction in the use of x-rays, particularly for pregnant women. No longer was it a procedure that could be treated lightheartedly and used for trivial purposes.
If it isn't a piece of candy stuck in Junior's throat.
One minor casualty of this increased concern was the disappearance in the early 60s of a familiar sight in shoe shops, an x-ray machine for children to wiggle their toes under. Even though the doses were very low, the view was growing that perhaps all radiation, however low, had some harmful effects.
Now, when we get down to the risks of very small doses, the argument is about whether there is any radiation dose which is safe. Is there some dose of radiation which produces no long-term harm at all? Is there a threshold, in other words?
So, 40 years into the atomic age, we have a very detailed knowledge of the effects of high and medium doses of radiation. But we still can't say precisely how many cancer deaths result from the small but regular additions to the natural background radiation. So that's one question mark that hangs over the nuclear power industry. Another is the possibility of the catastrophic failure of a nuclear power station. Hinkley Point Power Station in Somerset, one of Britain's advanced gas-cooled nuclear power stations. These men are going through what's called the pile cap to examine layers of insulation inside the massive reinforced concrete containment vessel. They're in full protective gear, and like divers, they're breathing air fed through lines into their face masks. This is the reality that distinguishes the nuclear power industry from any other. You can't have nuclear power without radiation, and radiation is damaging, potentially lethal, to human beings. And that fact dominates every aspect of this industry, right the way through from the design of the reactor and containment to the details of daily life on a nuclear power station. You can't, for example, leave the nuclear reactor building at any time without having your whole body scanned to see if you've picked up a radioactive particle. So you enter the scanning unit, you put your feet on the grills provided, put your hands in these slots, press forward, and there's a light above saying that it's checking now, checking the front. Green light comes on saying turn. Same grills, press the buttons, now scanning the back, light saying it's checking, and clear, or recheck. Doesn't like me, checking, clear. Then, and only then, can I go out through the gate. So it's a constant reminder of the threat posed by even small amounts of radiation. And that's precisely the problem that confronted the world's first nuclear power station engineers back in the late 50s. They had to design and build a machine that would create literally millions of lethal doses of radiation, yet ensure that nothing more than very small amounts would ever be released into the environment, either during normal operations or as a result of an accident. It was a daunting, even an overwhelming task, yet they approached it somehow with immense confidence. There was a tremendous amount of optimism around in those early days of the Magnox program. To be a nuclear engineer was a bit like being a test pilot. They were working in a brand new technology. They were right at the sharp end of knowledge in all sorts of fields, such as metallurgy, for example. And they were being asked to provide precision engineering on a macro scale, a bit like building a watch that weighs 20-odd thousand tons. What's more, it's a very dynamic watch. The whole thing expands and contracts with changes in the temperature of the core. The sheer weight of many of the components imposes major gravitational stresses. There are the vibrational stresses set up by the 130 tons of coolant hurtling through the core at over 100 miles an hour. And to add to those purely engineering problems, there are the specifically nuclear ones. The fact, for example, that everything in the core is subjected to intense neutron bombardment. And one significant problem that has arisen is the effect of that neutron bombardment on the crystalline structure of the graphite in the core.
Subject to intense radioactive bombardment, the graphite does tend to change shape over a period of time. This is because the actual atoms of the graphite itself are displaced by the nuclear bombardment. And as graphite, as we know from our use of pencils and so on, is a slippery substance. It consists of layers which slide one upon the other. If these atoms are displaced, that process is prevented, and it does in fact lead in some cases to shrinkage and in some cases to expansion. In other words, a change of shape of any particular piece of graphite you have in the core. The implications are that the graphite stack in the reactor itself has hundreds of channels in it which contain the nuclear fuel and the control rods. And clearly, if those channels change shape too much, they could inhibit the entry of the control rods, which are there for safety purposes, and in fact make the loading of the graphite core itself with nuclear fuel more difficult.
Now, apart from problems related to the malformation and even the breakdown of the essential graphite in the core, there's the whole question of inaccessibility. Once this reactor is up and running, whole areas become inaccessible, so you can't easily get in to find out what's gone wrong or to put it right. Relate that to the corrosion that can occur when the reactor is working at these temperatures and pressures, and that can suddenly make even apparently minor components like a bolt or a washer very significant indeed.
In 1968, we'd been running these reactors at Bradwell for about 6 years, quite successfully. One day during that year, we were carrying out a normal refuelling operation when we encountered some difficulty getting hold of a fuel element. What transpired was that a nut and bolt securing an item above the reactor had in fact fractured and fallen onto the fuel element. That was really the beginning of quite an interesting story. Investigation showed that the nut and bolt had been suffering from a form of steel oxidation, corrosion you might commonly call it.
And when these pieces were recovered and examined, it was obvious what had happened. The oxide had got between the washers and the faces of the nuts and bolts and had expanded and failed the bolt. It is a fact that the oxide takes up rather more space than the metal from which it comes. You add oxygen to the iron, it creates iron oxide, and that occupies a rather greater volume than the metal from which it was made. The oxide gets between the washers and the bolts, strains the nuts, and eventually, if you allow it to go on long enough, will fail them.
We decided that one thing which we'd already seen happen, nuts and bolts breaking, could lead to the unfortunate occurrence of debris around the top of the reactor. It was also clear that we had to guarantee the top of the reactor would continue to be held securely and rigidly together. Both of those potential problems required, we decided, some significant engineering work.
You couldn't, of course, just send men in to change the bolts.
That's where, in the case of a Magnox or any nuclear reactor, the problem really begins. Because we're standing here 40 foot above the top of the active reactor where these particular problems manifest themselves. Any engineering work that we had to contemplate could only be carried out 40 foot below where we're standing, operating the tools from this point, access down a 10-inch diameter hole.
So that was the only kind of access you had then?
That's right. No question of anyone being able to go into a nuclear reactor after it's been at power.
So what did you do about it, given that you couldn't physically go in and actually change those bolts?
The basic mechanism was to lower the temperature of the gas. We found that this phenomenon was very susceptible to temperature, and a relatively small lowering of the temperature by a few tens of degrees was sufficient to prevent the phenomenon occurring.
The decision had to be taken to downgrade the reactors, to downrate them, so that they were no longer operating at as high a temperature and therefore not producing as much electricity. And since they had already cost considerably more than competitive fossil fuel stations would have cost, according to then Sir Christopher Hinton of the Central Electricity Generating Board, this downrating made them even less economically competitive than they would have been before. And the industry, I think at that stage, the planners of the industry experienced their first major spasm of uncertainty.
After the spasm of uncertainty over the Magnox had rippled through the industry in the late 60s, there was growing pressure for a second generation of nuclear power stations, bigger in terms of power output, far more efficient in terms of design. The real limitation of the Magnox stations is the solid uranium fuel. It can operate only at relatively low temperatures, so to increase the power output of the station, you can't raise the operating temperature, you have to increase the size of the core. And after a short while, the sheer size of the core becomes a limiting factor. So there was a need for a fuel that could operate at far higher temperatures. They chose a ceramic fuel, in fact uranium oxide, compressed into small pellets about the size of a licorice ore salt, stacked in thin-walled stainless steel pins. The pins were gathered in clusters inside this graphite sleeve. The fuel was in fact enriched uranium, which means it had a far higher density of those fissionable uranium-235 atoms. The cooling gas remained carbon dioxide, and the design was known as the Advanced Gas-Cooled Reactor. This is the first of the advanced gas-cooled reactors to go on stream in the UK at Hinkley Point in Somerset. It started operations in 1976. Since then it's been joined by 3 others in the UK and 1 at Hunterston in Scotland, and 2 others are under construction. How different is it from the Magnox design? Well, it shares the 2 fundamental features of a huge graphite moderator block in the core, and the coolant gas that carries the heat from the core to generate steam is still carbon dioxide gas. After that, the differences are pretty radical. All the AGRs, as they're called, for example, are wrapped in a massive reinforced concrete structure 6 meters thick and lined with steel that serves both as a pressure vessel and as a biological shield. And because of the ceramic fuel, the uranium oxide fuel, it's altogether a fiercer and a hotter beast. The carbon dioxide coolant, for example, is circulating through the core at around 100 miles an hour. And because it's under pressure, it has something of the consistency of hot treacle. It actually leaves the core with a temperature of 650 degrees centigrade, almost twice that of the Magnox reactor. And those higher temperatures are what the engineers wanted to achieve better operating efficiencies. That's not quite how it's worked out. In fact, the best of these stations is achieving only something like 60% of the designed output, and it doesn't look as if that figure will ever be significantly improved upon. They've also run into a whole host of engineering problems, partly because the engineers believed they had the knowledge and the skills to build working power stations that were 20 times larger than the small experimental gas-cooled reactor from which the design has been taken. In the event, that belief was shown to be grossly in error. The other main problem has been the actual construction phase itself. These power stations aren't mass-produced, they're handcrafted, as it were, on site, and that has led to endless changes and delays.
OK, George, just drop it now.
Now, there's another major reactor type we haven't talked about so far. It's this one behind me here, the pressurised water reactor, or PWR. The CGB have been trying to introduce this type into the UK for the past 15 years or so, and they argued its case fiercely at Sizewell. It's an American design, derived essentially from the nuclear power pack of American nuclear submarines, and by far and away the most widely used reactor type around the world. It differs radically from the British Magnox and AGR designs. It uses water as a coolant rather than carbon dioxide gas, and it has a very compact core. This makes it quite a different kind of machine to control. Everything happens more rapidly. Now, at the heart of the reactor is a massive steel pressure vessel 30 centimetres thick. It's in the centre at the bottom of this picture. It contains the fuel rods and it's filled with water. Water under immense pressure, about 2,000 pounds per square inch. There are massive pumps to force the water through the core and then away to the boilers, or steam generators, where the water gives up its heat to create steam, before it flows back through the core again. An important point is that all the so-called primary systems, the core, the pumps and the boilers, are contained within a massive reinforced concrete steel-lined building that is sealed when the reactor is in operation. People only go in when the reactor is shut down for maintenance. Now, the question mark over this reactor is over its safety, because if anything happens at all to interrupt or to stop that flow of cooling water, then the temperature of the core rises very rapidly indeed, in minutes rather than hours. So there's immense concern over the emergency systems to keep that core temperature under control. Control is a word that hangs over the industry like the sword of Damocles. Control rooms in nuclear power stations are like a huge electromechanical brain. measuring and monitoring every heartbeat, every pulse and every flow in the reactor body. Any divergence, any movement away from the norm has to be caught and checked and corrected. Now, many engineers believe that compared with the PWR, the British Advanced Gas-Cooled Reactor is inherently far safer. It has what they call high thermal inertia. If anything goes wrong, the temperature changes only slowly. There are hours rather than minutes to make decisions. But however inherently safe it may be, as with any other man-made system, of course, all sorts of things can go wrong. Now, defining what those things might be has been something that's occupied the engineers here for the past 15 or 20 years. And that, taken together with an analysis of all the incidents that have taken place, has led to the production of what might be called, I suppose, a safety tree. It's a series of actions or responses, one backing up the other, all designed either to shut the reactor down or to keep it within certain temperature limits. OK, here we are in the control room. It's on full load, humming along nicely, all the dials in the right place. Let's play devil's advocate for a minute and arrange a few disasters. Well, just about the worst thing that can happen is a major loss of coolant accident, with the carbon dioxide gas spewing out into the plant, say, rather than cooling the core. But once the systems here had detected the drop in pressure, then the control rods, which are suspended above the plant, would automatically drop down into their channels. They're made of boron, they have a voracious appetite for neutrons. They would close down the fission process in a matter of seconds. Of course, the core would still be very hot. It would still need some cooling, but it wouldn't be getting any hotter. If there was a power failure, then these control rods are suspended on a giant electromagnet, so they would drop down to their channels under the force of gravity alone. Now, if for some reason the control rods won't go into their channels, say there's been an earthquake and the reactor's been shifted sideways, the secondary safety system is to flood the reactor core with nitrogen. It has the same sort of appetite for free neutrons and would close the fission process down. If all that fails, then the final resort is to flood the reactor core with water, but that would mean writing the reactor off. And that's just one safety tree among many. There are, of course, backup power systems, backup instrumentation systems. The power cables are run in differently routed channels, so a fire in one part of the plant doesn't cut off power from the rest of it. There is, as there should be, immense concentration on safety. But as we all know, nothing is foolproof. The finger can always press the wrong button. Something can always go wrong. Take, for example, this little hatch. This is the bottom of the reactor, and the hatch covers the end of what's known as the inlet guide vane shaft. The guide vane itself controls the flow of the vital coolant, the carbon dioxide gas, into the bottom of the reactor. If there's a power failure, the shaft may have to be operated manually. Now, towards the end of last year, 2 operators came along as part of a routine inspection and removed the hatch. As they did so, the shaft itself, made of steel, about 4 feet long, 1.5 inches in diameter, shot out and landed on the floor, closely followed by about 14 tons of lightly radioactive carbon dioxide coolant gas, about 1/10 of the total charge of gas in the reactor. What had happened? Well, a nut had fallen off the end of a small retaining bolt. Now, the reactor itself wasn't in any danger. In fact, it was shut down at the time. The alarm bell was pressed to get the men out of the way of the suffocating carbon dioxide gas. But what it shows is how small the thing has to go wrong to vitally affect the operation of so big and sophisticated a machine. Even so, mechanical failures can to some extent be predicted. Certain human ones can't.
And then, of course, there are things that could go wrong that you can't anticipate at all, and they don't figure in the fault tree at all. They're just not there, as there's not even a box and a number attached to them, and yet they can go wrong. The nice one that I know of at a nuclear power station was labourers at the construction stage urinating into the housings. They're up on a very high scaffold after lunch, and rather than come all the way down from the scaffold, there are these little openings in the concrete that they're forming just at the right height, and so they use those, which are actually going to have reinforcing cables threaded through them to hold the whole containment vessel together. And so it was discovered that some of those cables were corroding much more rapidly than they should have done, and this was the cause.
In the sleepy little town of Harrisburg, Pennsylvania, just after 4 o'clock on the morning of the 28th of March 1979, red lights began to flash in the control room of reactor number 2 at the 3 Mile Island nuclear power station. It's a pressurised water reactor, so it has two water circuits. The primary system, shown in red here, circulates through the core and carries the heat away to the boilers on the right, where it gives up its heat to the secondary system, shown in blue, that turns water into steam to drive the turbines. For some reason, there was a loss of pressure in the boilers, so on cue, the emergency pumps came on automatically to pump more water into the boilers. Unfortunately, they couldn't. A key valve had been left closed. So more lights began to flash in the control room. There was a crew of 10 on duty that morning. 4 were licensed reactor operators, 2 of whom were in charge of the control room. So they had about 24 panels, about 2,000 instruments and dials, telling them exactly what was going on in the reactor core. Now, this is a PWR control room, not in America, but in France. A Westinghouse design, so very similar. Many of the dials and gauges are exactly the same. In fact, many of them are changed after what happened at 3 Mile Island. But there, within a few seconds of the emergency starting, there was a cascade of over 100 alarms sounding off. So how could they begin to decipher what was going on inside the reactor?
In a way, you can compare 3 Mile Island to an ordinary domestic heating system with an airlock in it. Now, when that happens, you get some weird events. The cold tap sometimes produces hot water, other taps don't work, and so you run up and down the house, and eventually you get an idea in your mind as to where the airlock is, and your plumber, with some luck, might be able to do something about it. What happened in 3 Mile Island was a similar thing in a far more complicated system where decisions had to be made very quickly. And so what the operators did was, mentally, try to figure out where the blockage and where the airlock was. Staring at all those dials, they made a decision which turned out to have been the wrong one. But the basic idea was, let's find where the blockage is in our minds and let's have an idea of what the system is doing. And in a way, 3 Mile Island was an invisible event.
Meanwhile, back at the reactor, a safety valve had opened at the top of the system to release pressure. The primary coolant, the red circuit, was getting hotter and hotter and expanding, so pressure was rising rapidly. The valve released steam precisely as it was supposed to do. The trouble is, when the pressure in the system had dropped, the valve stayed open. Now, that stuck valve misled the operators for 2.5 critical hours. They tried everything they knew, but they just couldn't fathom out what was happening in the reactor core. As one of the operators said, I don't know why the pressurizer level was indicating so high or why the pressure was holding low, but we seemed to be fairly stable. And all 5 of us in there were simply trying to put our heads together to understand the weird indications we had. And in the rather more formal words of the report, they say there's no indication that the operators knew the basic theory of pressurized water reactors. That is, hot reactor coolant remains as a liquid only by keeping the pressure up, as in a household pressure cooker. It should have been understood that when the pressure gets low, then the hot water in the system will boil. And boil it did, at which stage the secondary emergency core cooling system came into operation. It's at the bottom of the core, and it's designed to pump water at high pressure directly into the primary coolant circuit to ensure that the temperature of the core is lowered. But by now, the operators were thoroughly confused, and they switched the secondary emergency cooling system off. They had so many apparently contradictory indications, they completely lost control of the situation. Meanwhile, inside the reactor, there was now insufficient coolant. The core itself had begun to melt, and an immense bubble of hydrogen had formed inside the steel pressure vessel. The fear was that it would blow the reactor apart, and so release the deadly fission products into the environment. Fortunately, that didn't happen. But all the time, there was great confusion in the way the information was fed out to the public. For example, at one stage, a release of radioactivity was announced that hadn't occurred. Evacuations were ordered, cancelled, and then reordered. At 2 press conferences, almost simultaneously, completely contradictory announcements were made. And of course, there was great panic throughout the entire area. For example, people rang from New York, 200 miles away, to see if they should evacuate their houses. And terminally ill patients rang in to see if they could help by going into the high radiation zone. Great panic, immense confusion from start to finish.
What 3 Mile Island did was it killed an illusion, the illusion of absolute safety in the nuclear power industry. That's why we remember it. No one died, perhaps no one was influenced in any way, but an illusion died, and that was a very important learning experience.
Some people describe it as a damn close-run thing. Others say the safety systems worked despite everything the operators did. But however you describe it, until the events at Chernobyl a few weeks ago, it was unquestionably the worst nuclear disaster the world has ever seen in 30 or more years of operation. In the same breath, one can say that no one died at 3 Mile Island. Marginal doses of radiation were received. When you compare that with what happened at Flixborough and at Seveso and Bhopal, and you think of the crash of the Japanese airline 747 last year that killed over 500 people, the daily carnage on our roads caused by drunken drivers, one has to say that we set nuclear power aside in some way. On the one hand, we have all the other risks we take in our lives. On the other, we have nuclear power. And the question is, can it ever close that gap, particularly in the light of the events at Chernobyl, where the civilian nuclear power industry has killed people, and where people are dying even today in the hospitals in Kiev?
The evidence, insofar as we've got it, indicates that Chernobyl was a serious but not catastrophic accident. It could have been far worse. It is quite possible for nuclear power stations to generate far more danger to the public than Chernobyl did. So the kind of irony is that Chernobyl was bad, but nothing like as bad as it probably is in the minds of a lot of people. And that, in a sense, is a hard business for the nuclear industry to have to tolerate. But when we come to the impact on the public, I think we can divide it into 3. The first one is that the people actually begun to think about nuclear energy in a serious way for the first time, because our own little accident in Windscape, which was bad enough, was, as we all know, very much suppressed by the powers that be. And there was no real criticism of nuclear technology back in the early 50s and mid-50s, and therefore there wasn't anything like the same kind of disquiet as you get in the late 80s. The second thing is that people really have begun to realise just how dangerous nuclear power is when it is unleashed and goes wrong. And that, I think, is a very important and very significant factor. In other words, there is this believability in the catastrophe. And the third one, probably the most important, is that they no longer can believe the assurances of the industry that things are so safe that it can't happen here. There is no such thing any longer in the public's minds as things not being able to happen. Things have happened, things could happen, and they believe it. And therefore the industry is almost in a hiding to nothing in trying to argue its case that we have probabilities of 10 to the minus 7 of accidents of this kind, because it's a meaningless figure for most people, and they actually don't believe it anyway.
Mr. Ryder, in the light of Chernobyl, do you think that nuclear power is now too hot to handle?
I think that's basically a question for the politicians. I mean, my job is to assess the risks in engineering terms and in consequential terms. We can help the politicians to understand the problems, and at the end of the day they have to decide whether those sort of risks are acceptable in the society we live in for the benefits that it gives.
Next week in Too Hot to Handle, we examine whether those benefits carry too great a risk.
Technically speaking, nuclear power is one of the safest industries we've got in this country in all its aspects. And yet there is a common feeling of uncertainty, of concern, of apprehension about it and about radioactivity. And I would spend a lot of money to to take that fear away from people, because it's fear which isn't justified.
On a cool spring morning in Leicestershire, a train is being prepared for its last journey. This journey has only one purpose: to dispel fears about the transport of nuclear waste by rail. The spent fuel is carried in 50-ton steel containers, and one of them has been laid at an angle across the tracks. The aim is to show that it can withstand what is perhaps the worst kind of accident it's ever likely to encounter. The 240-ton train hurtled into the container, but the container remained sealed. Now, when the Central Electricity Generating Board is prepared to say publicly it would spend a great deal of money to allay public fears over radioactivity, it's clear those fears are beginning to bite. There's a lot of concern in high places. And the setting up of that dramatic and horrendously expensive demonstration in front of hundreds of reporters and observers is an indication that, to some extent at least, they're prepared to put their money where their mouth is. Now, at this precise moment in time, the CEGB is more than ever concerned to allay public fears about nuclear power, because it's keen to get started on a whole new programme of nuclear power station building, using the American-designed pressurised water reactor, or PWR as it's called. And the very first of those PWRs is designed to be built here, next door to a Magnox station on the coast at Sizewell in Suffolk. Now, the name Sizewell has really passed into nuclear folklore because of the massive public debate over the building of this reactor, the immensely long drawn-out trial, as it proved to be, of nuclear power in this country, which served to bring into sharper focus than ever before the huge gulf there is between the public on the one hand, with its fears and anxieties about nuclear power, and the scientists with their cool calculations of what dangers it brings. And this programme is focused precisely on that area: the public perceptions and the scientists' calculations, how they evaluate the dangers, how those risks compare with other risks that we take as a normal part of our daily lives. Now, for many people, of course, what happened at Chernobyl 6 weeks or so ago sweeps aside all argument. Whatever they say about it couldn't happen here, if that is the risk, then nuclear power is too dangerous at any price. But is it? Before Chernobyl, one of the main focal points of public anxiety was the waste material, the stuff that's left when the uranium is spent 6 or 7 or even 10 years inside the reactor core. Most of the fuel rod's readily available uranium atoms have been split, used up, that is, during stay in the core. So when it's removed, it contains a whole variety of highly radioactive substances, most of which are no use to anyone. But in each rod, there is plutonium and a certain amount of unused uranium. Now, in the UK, from the very earliest days, the spent fuel has been carted away from the power stations to Sellafield in Cumbria for that plutonium and uranium to be recovered.
CEGB, in a sense, has had the easy ride here. I mean, we run the reactors, we put the fuel in the reactors, it gets very radioactive as a result of that. We then put it in a large irradiated fuel flask, very robust box, and we put it on a railway train and we wave goodbye to it, and off it goes to Sellafield, and that's their problem.
About 10 times a day, one of these waste containers or flasks arrives at Sellafield from one of Britain's nuclear establishments. It's one of only 2 or 3 places in the UK able to handle the fearsomely radioactive fuel rods, and it has become a major foreign currency earner by reprocessing spent fuel from other countries. Sellafield is operated by a company called British Nuclear Fuels, BNFL, and its complex chemical treatment plants separate the waste into various categories. High-level waste remains very hot and intensely radioactive for thousands of years. This is stored on-site in the form of a sludge, although plans are underway to convert it into a form of glass to make it easier to contain. Intermediate waste, as it's called, is nowhere near so hot nor so intensely radioactive, but it still remains active for thousands of years. It's also stored here at Sellafield until they can come up with a better solution. One of the inevitable results of this treatment of radioactive fuel is the release into the environment of certain amounts of effluent. This is true of all chemical processes, not just Sellafield. However, in Sellafield's case, the effluent, in the form of gas and liquids, is radioactive. The amounts are small, and they're carefully measured. But Sellafield has an appalling record over the past 10 or a dozen years of getting it wrong, of allowing accidental releases, and quite rightly, they've been duly hammered for it in the press. Moreover, Sellafield has been charged publicly with causing leukemia in the local population.
Seascale village, with a population of 2,000, is just a mile and a half from Windscale. Here, since 1950, the year that Windscale began its operations, we found 11 cases of childhood cancer. Of these 11 children from Seascale village, 7 were victims of leukemia, the form of cancer most easily induced by radiation.
Radiation is the only known cause of leukemia at present, and the programme presented evidence to show that there was an abnormally high incidence of cancer, particularly leukemia, among the children of this small village of Seascale in Cumbria. 6 cases of leukemia in 30 years, 14 times the national average. Now, Seascale is the closest village to Sellafield, the plant where the British nuclear power industry washes its dirty linen, so to speak. This is where all the spent fuel is reprocessed. And most of the radioactive emissions from the nuclear power industry come from this plant. Although, as the Sellafield management are keen to point out, these emissions are still well below the authorised levels, the levels set by the international authorities.
Now, many industrial processes put out cancer-causing substances, but it's still emotionally unacceptable to learn that a commercial operation might be causing the deaths of innocent children from cancer. The newspapers have pursued every detail of the story, but have they dug deeply enough?
If we accept the circumstantial evidence, Seascale seems almost like an open and shut case. But is it? This is another northern town, this time in Northumberland, the little mining town of Ashington. And it was the site of another leukemia cluster. In this group of narrow terraced houses, 5 people died of leukemia in the space of just 3 years. What was the cause? Once again, no one really knows. But one thing is certain, it wasn't nuclear power, because this leukemia cluster occurred in the early 1930s. The point I'm really trying to make is that leukemia clusters in this country aren't widespread, but neither are they rare.
The fact is they occur in many places all over the country, and it has to be pointed out the vast majority of them, like this one in Ashington, are nowhere near nuclear installations.
But back to the Seascale controversy, and the Yorkshire television programme led to a widespread demand for an inquiry, and a commission was set up under the chairmanship of Sir Douglas Black.
Now, the Black Inquiry acknowledged that there were more cases of leukemia than you would expect in the small community of Seascale, but they pointed out that the children of the village were exposed to tiny amounts of extra radiation, amounts that had never been shown to cause leukemia in other situations where people had been similarly exposed. They concluded by saying in their report, "We can give a qualified reassurance about a possible health hazard to the people who are concerned in the neighbourhood of Sellafield." The Black Report set in motion more research designed to explore this mystery that underlies leukemia. One such project is based in Newcastle.
Well, I think it's a natural assumption to try and make that if you do have a high rate of leukemia, say, in a village which is less than a mile away from such a huge nuclear facility, and when one knows that the only known cause of leukemia is radiation, it's difficult not to associate the two. The problem is that we don't, although radiation is the only known cause of leukemia, it probably only accounts for a very, very small number of the cases of leukemia. And the vast majority of cases of leukemia have probably nothing at all to do with radiation.
The problem is to see whether it's possible to pinpoint a cause for the Seascale leukemias or whether they could have arisen by chance. Now, there is a major difficulty in establishing accurate disease rates for small communities, and in Seascale there are only 400 children, and they're part of a changing population that comes and goes over the years. So if only 1 or 2 cases of leukemia arose by chance in a group this small, it would produce a rate many times the average rate of 1 in 2,000. But the fact is that with most rare diseases, they never spread entirely evenly around the country.
Any rare disease, both cancer and other rare illnesses tend to cluster. I think that the last thing that one would expect from a rare disease is that it would be equally distributed, 1 in each ward. Rare things don't happen like that. Rare things tend to come in clusters.
Now, if the leukemia clusters in Cumbria were caused by nuclear power, you would expect to see clear patterns of distribution around the nuclear installations. Otherwise, you would expect a random distribution. Dr. Kraft and his colleague Stan Openshaw are examining leukemia data for the whole northeast of England.
Well, now we'll look at observed data. This is real occurrences of children with leukemia by wards in the northern region. And the wards have been ranked in terms of their unusualness. So the wards that appear first are the ones which have a leukemia occurrence rate, which is very unusual.
The data they've gathered so far confirm that the C-scale area, shown as green on the computer screen, still has the highest leukemia rate. But in Northumberland and Teesside, there are several communities, a long way from nuclear installations, that also have leukemia rates many times the national average. It's a pattern that is not easy to interpret, but it doesn't equate with nuclear power as being the cause.
I don't think anybody can say that there isn't a causal link. I think all we can say at the moment is that it does seem to be very unusual. The very high incidence of leukemia in C-scale is statistically very unusual. But exactly what that means, I don't think anybody can truly say.
The problem for all of us is that we're really caught in a crossfire. We get conflicting advice and information from all sides. On the one hand, for example, we have people like Greenpeace and Friends of the Earth saying this industry is poisoning the seas and the air around us. It's poisoning our environment. On the other hand, we have scientists employed, for example, by the National Radiological Protection Board and the Ministry of Agricultural, Fisheries and Food, genuine, honest men who are charged to safeguard our health in these areas, saying nothing of the sort, that nothing we're exposed to from the nuclear power industry reaches anything like the levels we get from natural background radiation. So who are we to believe? Well, the easy way out, of course, is to assume that the government scientists are bought men. But fortunately, we're not just dealing with opinion here. This area is susceptible to very precise scientific analysis.
Now, one of the greatest fears of radioactivity comes from the belief that scientists don't know much about it, and therefore there may be unpleasant surprises in store. That is not in fact the case. More is known about radiation than many other pollutants from the chemical and fertilizer industries, for example. What's more, radioactivity is unlike almost any other toxic substance in our environment. It's very easy to detect in extremely small amounts. Take Sellafield's emissions, for example. These are usually well below permitted limits. How do they know this? Well, because even though they spread all over the place in the air and the sea, they can be traced easily and measured very precisely. Let's follow the process through. Thousands of cubic metres of gas and water are discharged after they've been used as part of the reprocessing activities. These contain minute amounts of the atomic debris from the reprocessing of the fuel rods. Now, if we go back to the fission process in the reactor core, the splitting of the uranium-235 atoms and the release of neutrons and other particles leads to the creation of other radioactive elements. Elements, that is, which themselves can give off alpha and beta particles and gamma rays. Cesium, iodine, ruthenium, plutonium, and many others. When these substances pour out of the pipeline into the sea near Sellafield, they add small amounts of radioactivity to the environment. An environment, remember, that is already radioactive from natural elements like uranium and thorium. But because the scientists know very precisely which atoms are the products of nuclear fission, they can trace very accurately what contribution they make to the overall radioactivity. Let's take ruthenium as an example. These atoms lose half their radioactivity in a year or so, and that's a very important point in the control of the total amount of radioactivity this element adds to the environment. So, year after year, atoms of ruthenium are released into the sea. And because of the very high rate of decay, the annual release and the cumulative total radioactivity due to ruthenium over the years follow very much the same curve. Now, if we look at plutonium, 90% of it falls to the seabed and it remains radioactive for a very long time, thousands of years in fact. Now, this means that even though the annual releases have been kept at a very low level, the total amount of radioactivity in the environment due to the releases of plutonium over the past 30 years or so is much higher. Now, because of this, the annual permitted releases of plutonium are now being greatly reduced. But the important point, of course, is what of all this is likely to get back to man?
Well, the total quantities which will return to man, of course, are only a very small fraction of the amount which is discharged, and particularly when it comes to the shorter-lived nuclides, because they are physically decaying away before they can return to man. But the important thing is to have a good understanding of the concentrations which we will find in different seafoods relative to the concentrations in the ambient water and sediment, which are in turn related to the rate at which these nuclides are discharged from Sellafield.
Dr. Pentreath and his colleagues at the Ministry of Agriculture, Fisheries and Food have carried out detailed studies on the radioactivity of fish. Boat sets out into the Irish Sea on regular fishing expeditions for samples.
For the adult fish, we can estimate what sort of dose rates they would receive by knowing the distribution of the radioisotopes on the seabed, because the place spends most of its time sitting on the seabed. We can do better than that, in fact. We can attach to the fish dosimeters, little lithium fluoride disc tags like this, which are attached to a standard fish tag, a Peterson disc tag. This goes through the shoulder of the fish, and by measuring these little devices when they are returned to us from the fish which are caught commercially, we can estimate directly the dose which the adult fish have received.
All the fish and the other kinds of sea life that are caught on these fishing expeditions go through a detailed analysis, first of all in Whitehaven and subsequently in the main laboratory in Lowestoft. Because of the ease with which the radioactive elements can be traced, it's possible to build up a very detailed picture of where the radioactive elements that come out of the Sellafield pipeline end up and in what amounts. Now, as it happens, different forms of sea life absorb different elements. The elements also migrate to different parts of the environment. Ruthenium, for example, splits roughly half and half between the seawater and the seabed, whereas cesium remains almost entirely in the seawater and only a very small fraction drops to the seafloor. If we look at the other elements, americium, for example, ends up on the seafloor, and the same is true for plutonium, although a very small fraction of this element sticks to the plankton on the surface. Now, this distribution governs where the elements get into the food chain. Plaice, for example, take up plutonium and cesium. Lobsters, for some reason, concentrate americium in their tails and plutonium in their claws. Whereas sea crabs carry minute amounts of both these elements throughout their body. And if we look at the humble winkle, this takes up ruthenium, plutonium and americium. So to recap, by examining these sea creatures, the scientists know precisely the route whereby the radioactivity gets back to man.
But how do these people go about their job? They're charged, remember, with ensuring that none of us is exposed to unsafe levels of radiation. That only includes radiation from the nuclear power industry. Medical radiation and natural background radiation is not part of their brief. Now, clearly they can't go around and examine all of us, but they've come up with a very neat solution. They've identified groups of people who, by reason of their lifestyle, and particularly the kind of food they eat, are exposed to much more radiation than the rest of us. And by monitoring these people very closely indeed, and ensuring that they stay within the permitted levels, then, by definition, the rest of us are okay. Now, they call these people critical groups.
Over the years, these critical groups have changed. A few years ago, the scientists studied people who ate lava bread made from seaweed, which concentrates the radioactive elements. Nowadays, they're mainly interested in people who eat large amounts of winkles. They focused on this group, about 30 families who live on the Cumbrian coast, because a detailed survey showed that they were getting higher doses of man-made radiation than the rest of us. Although it's still important to underline, they're getting much less than the maximum permissible limits. Now, these people enable the scientists to monitor whether man-made radioactivity in the environment is being kept low enough. If it turned out, for example, that the winkle eaters were getting doses near the permitted limits, then the releases from Sellafield would have to be reduced.
Champion, get him out of the start.
So after following the plutonium from the pipeline to the sea and from sea to Winkle, the intrepid scientists had one more question. How much plutonium gets from the Winkle into man?
Here then go.
Good morning.
Been on fish?
What we did was to consume a relatively large amount of winkles, half a kilogram in one day, which was not an exactly pleasing prospect. In my own case, I ate one quantity for breakfast, which I just about managed to keep down. Ate a further quantity at lunchtime, which was even less palatable than the first amount, and then finished them off in the evening, literally by swallowing them whole, because by that stage I'd certainly had a belly full of winkles. In order to determine the quantity of plutonium which was transferred across the gut, and I should have said that these winkles came from the Sellafield area, so that they contained plutonium which the winkles had accumulated naturally in the environment. In order to determine the fraction which goes across the gut wall, what we had to do was to collect all of the urine that we produced over the subsequent 10 days. This we did, and the concentrations in our individual urine samples were so low that in fact we had to pool our urine samples in order to get sufficient quantities of plutonium to measure. Nevertheless, these measurements were done, and from it was calculated that the transfer of plutonium across the gut wall was of the order of 0.01%.
So, as far as the men from the ministry are concerned, they followed this particular radioactive element all the way up the food chain, and they're satisfied that even in the most exposed groups, the emissions from Sellafield haven't been shown to constitute a hazard.
In a sense, of course, it's very reassuring to know that these scientists are beavering away week in, week out, measuring the emissions from the nuclear power industry, what's more, tracing those emissions through the biological pathways, making sure they know what happens to these substances, and ensuring that no one, not even the critical groups, reaches anywhere near the permitted doses. If they were to reach, for example, even half that maximum permitted dose, they'd be very worried. But it begs the fundamental question: who sets these permitted doses? Who says they're safe? Now, one of the most influential, one of the most frequently referred to organisations on the whole nuclear scene is the ICRP, or the International Commission on Radiological Protection. It's a truly international body in the sense it's made up of senior scientists drawn from all over the world. It was originally set up in 1928 to establish radiation safety standards for medical staff. But now its committees review all the latest research on radiation and recommend the maximum doses that any of us should receive, both on a lifetime basis and for each year. In the units in which radioactivity is measured, we all get on average 1 unit a year from the background radioactivity in the environment around us. The official limits permit a maximum of 5 more units in any 1 year from other sources. But they restrict the total additional lifetime dose to 70 units. And they don't concern themselves in any way with medical exposure. Now, most of us, and particularly the critical groups, get more radiation sometimes than others. But in any 1 year, the amount must not exceed 5 units, and the lifetime total must still be 70 or less. In practice, we get nowhere near the recommended annual dose limit. In fact, if you look at this graph, the actual dose received by the population of this country is about 1/5 of the recommended annual dose. Even when, as we have done here, we include medical X-rays. And when you look at how much of that actual dose comes from the nuclear industry, the thin yellow line, you can see it's a very small component.
In terms of numerical change, from 1934, I suppose, down to about 1950, those limits came down by to about 1/3. And from then until now, they've come down by to a tenth of the original figures. What's actually more important is that their intention has changed. They were originally, I suppose one might call them measures of ambition. They gave an indication of what ought to be achieved. From about the middle 1950s onwards, it's become increasingly clear that that's not the way they should be viewed, and they're now looked at very clearly as the levels which really ought never to be exceeded. They're certainly not an adequate measure of intention, and they have to be supplemented by very much more powerful requirements, of which the most well-known is the need to keep all doses as low as reasonably achievable, economic and social factors being taken into account. That is by far the most important feature of radiation protection these days.
So a picture emerges in which half of our radiation is received from entirely natural sources, rocks, cosmic rays, food and so on. Then there's a large component from radioactive gases that come from the ground but build up in our houses. So from these analyses of all the radioactivity we're exposed to, a picture emerges that puts the radiation from man's activities in some sort of context. And it turns out to be a rather surprising result. It seems that about 0.5% comes from former nuclear weapons testing. Another 0.5% comes from various things like air travel and luminous watches. And slightly less than 0.5% comes from various industrial uses. But right at the bottom of the list, there's 0.1% from the entire UK nuclear power industry. But even so, how harmful might that 0.1% be?
I think you have to take a lot of ifs into account if you're trying to look at the total detriment to European world population from the production of nuclear power and from the whole nuclear power industry in this country. Much of the dose to individuals would be at very, very low levels. And as we've said, we make the assumption that all radiation is harmful. And therefore, some individuals receive really very, very tiny doses indeed, where the likelihood for that individual of any detriment is very, very small. So what we have is postulated deaths. We have so much radiation to so many people. We're taking a straight overall risk factor and saying that's the number of deaths there well might be at the worst possible condition. We may well be doing much less damage than that.
It's been estimated that in this country, over the next 20 years or so, something like 30 or 40 people will contract cancer as a result of the emissions from the nuclear power industry. The problem is in knowing how to react to that figure, because, of course, there's no easy way. 30 deaths is 30 deaths too many. But during that same period of 20 years, something like 3 or 4 million people in this country will contract cancer from all the other causes. Many, of course, will be from smoking. Some will be from people who travel in trains and planes and cars with people who smoke. But how are we to assess the impact or the significance of those 30 extra cases, when in any case they can't be identified given the natural variation of the cancer figures? Obviously, people find some risks far more acceptable than others without a really great deal of concern about the figures. Risks over which we have no control, for example, are less acceptable than risks we choose to take, even if they're bigger ones: driving, smoking, rock climbing, hang gliding, and so on. And the plain fact is that if we're looking at the risk reduction per pound spent, then we can achieve a far greater result by concentrating on the medical field than we can on the nuclear one. Now, you may remember that about 10% of the average annual exposure to radiation comes from medical X-rays. That's not spread evenly across the population, of course, but about 4 people in 10 have at least 1 X-ray a year. Now, if we apply the same process of analysis to medical X-rays, as we do, for example, to the discharges from Sellafield or to the radioactive cloud that came from Chernobyl, then medical X-rays will account for about 1,000 extra cancers in the UK over the next 20 years. Now, you may argue, of course, that the benefits, the early diagnosis of disease, the accurate location of fractures and so on, are well worth that sort of price. But we've known for some time now that we can have all those benefits at a much lower level of risk and therefore fewer cancers if only we'd make certain changes. Now, when a patient has an X-ray, they lie on the table or the bed here. The beam, the X-ray beam, comes from above, and it has to be intensive enough to pass through the patient and the table to expose the film underneath. The table happens to be made of plywood. That is commonly the case these days. If, however, it were made of a material more transparent to X-rays, such as carbon fibre, it would knock about 10% off the radiation dose received by the patient. Even more important is the design of the cassette that holds the film. At the moment, that cassette is made of aluminium. If that were replaced by carbon fibres as well, it would further reduce the patient's radiation dose. Inside, there's a screen that fluoresces when it's hit by the X-rays. It's made of a substance known as calcium tungstate. If that were scrapped and replaced by a more modern screen, known as a rare earth screen, it would fluoresce earlier with fewer X-rays and therefore reduce the patient's radiation dose by as much as 30 or 40%. Add all those changes together, and you can reduce the average dose received from an X-ray by well over a half, and all at relatively little cost. And the general effect on the public would be the equivalent of, say, closing down a plant like Sellafield many times over, including all those accidental releases. But of course, if you compare the waste from nuclear power stations or radiation leaks from Sellafield with medical x-rays, there's no question which would grab the headlines. And quite apart from that, when it comes to assessing risk, we don't seem to work in any particularly rational or orderly way. We rarely, if ever, make any sort of accurate calculation of the odds. We live by a constant kind of rule of thumb. And the perception of benefit or convenience is a very important element. Life, as they say, is a dangerous business, and driving is one of the most dangerous bits of it. We've had the car now for around 100 years, and essentially we've become addicted to it. Difficult, in fact, to see how we could arrange our lives without it. It brings so much convenience. But of course, the car is a killer. In the UK alone, it kills around 6,000 people a year and injures in some way around 315,000. So that's the scale of the risk, death or serious injury. And I think one might argue that for that level of risk, then no convenience is worth it. It only makes sense when we take the probability into account. And the probability of being killed or injured is around 1 in 1,000. Now, we never know that figure. We certainly never make a sort of conscious calculation. We receive information from all sorts of sources and make a general estimate. And then we say, for that level of risk, then we want the convenience of the car. But what exactly does 1 in 1,000 mean? Well, one common method is to take the figures on road accidents, and on deaths and injuries in those accidents, and to divide these into the readily available figures on the number of car journeys in any one year. What this means in practice is that whenever you start up your car, there are very precise odds on the chances of being involved in an accident or of being killed or injured. Now, the same sort of thing applies to flying, normally estimated on the number of passengers killed or injured divided into the number of passenger miles flown. And you can do the same sort of thing for any activities, from being killed in a hotel fire to being injured crossing the road. So those are the two key factors in our assessment of risk, the scale of the risk and the probability of its occurring. But when we look at familiar events like driving and flying and smoking, for example, all sorts of other factors come into play.
Now, there are three ways in which people approach this. The first one is a familiar type of danger, such as a damage to yourself in the house when you fall off a ladder or electrocute yourself, or driving a car and getting involved in an accident. In that kind of risk, people often see it as a matter of carelessness. That is, they say, it's my fault, I made a mistake, I took a chance, I didn't think ahead, and therefore they get hurt. And they really blame themselves. There's no blame to the technology, there's no blame to anything that went on in the house, for example. The second one is when something happens where you feel that there's nothing whatsoever to do with you, it's just a piece of bad luck. Someone overtakes and you happen to be in the way and you get killed, or you're in a plane and the plane crashes and you say, or if you're still alive, you say, that was tough, it was not my fault, and that was just fate at work. And both of these people accept, because they tend to see that form of risk as something which is part and parcel of existence. But the third kind of risk is the risk which is involuntary, which is imposed upon them by something which is alien to them and something that they actually don't particularly like. And therefore you're talking about a form of risk which they believe is unacceptable because it is imposed or enforced on them, and they do not feel powerless. They feel too powerless to stop it. They actually want to do something about it, but they feel unable to stop it. And when it happens, they feel that they are innocent and tragic victims of something that they really dislike. Now, that form of risk is the one which focuses in on nuclear power.
The average man will accept high risks if he has the steering wheel in his hands. At over 50 miles an hour, there's relatively little you can do to control a crash, but people feel comfortable with it. Yet if you put that person in the passenger's seat, then they feel tense. They certainly feel tense in aeroplanes where they aren't the pilots themselves. We can show experimentally that people will reduce their level of anxiety in any risky situation if they have control or they have the illusion of control. So I think control is one of the essential features about radiation, in that we don't have control over it, it's done by other people. So we're immediately in the passenger position, and that makes us anxious.
Well, one incident of which I heard many years ago displays very clearly how we view risks in different ways according to how they occur. In Sweden, a very well governed and very well statisticized country, it was decided for scientific reasons to send off a lot of sounding rockets in the auroral zone. in an area sparsely inhabited by labs. Now with sounding rockets, you send up a lot of devices and a good deal of the ironmongery falls back to Earth. And of course, were it to hit somebody, it could be fatal. And so normally in areas where frequent sounding rocket campaigns take place, one builds shelters for the population. This was to be a once and for all 2 weeks, so that wasn't worth it. It was decided to evacuate the population instead. And this was done. They were taken by helicopters to hotels in Luleå. Everybody had a fine old time, and they came back 2 weeks later in helicopters. But if you work out the probabilities, then the chance of somebody being hit by a piece of sounding rocket is much smaller than the chance of a helicopter accident.
But how, if we look at man in relation to risk, one thing stands out above all else, and that is the fact that there's naught so queer as folk, that man is an irrational, emotional, arbitrary animal. If someone falls down a well, for example, or gets trapped in a mine shaft or stuck on a mountain, no effort is too great, no expense must be spared in trying to save that life. And if the life isn't saved, there can almost be a kind of national mourning. On the other hand, we turn a blind eye to the daily carnage on our roads, even when much of it is caused by something as irresponsible as drinking and driving. Now, where in all that sits our fear of the risks of nuclear power? On the one hand, we have the precise mathematical calculations of the scientists that, taking into account the effects of safety systems, really put the risks of our being killed or injured by nuclear power at a very low level. On the other, we have the overwhelming fear of the single major catastrophic event.
At about 5 o'clock in the afternoon of the 1st of June 1974, part of the Flixborough chemical plant near Scunthorpe exploded into a fireball. 28 people in the factory were killed, 36 seriously injured, and 2,000 houses and other buildings nearby were badly damaged. By any standards, a major disaster. And there are over 1,500 installations like Flixborough handling hazardous chemicals in this country, many of them near major conurbations. And the history of the coal industry is, of course, littered with mining and other disasters. On the 21st of October 1966, in the village of Aberfan in South Wales, an abandoned slag heap overlooking the village collapsed onto the school, killing a whole generation of the village children. 144 people died in the disaster. And in London, during 1 week in the winter of 1952, nearly 5,000 people died from breathing the smog caused by the burning of coal in our power stations. It was never catalogued in that way, but it was a disaster coming directly from the way we chose to generate our electricity, and indeed still generate the biggest proportion of it. A big modern coal-fired power station, such as Drax in Yorkshire, burns 37,000 tonnes of coal a day in its giant furnaces. And it puts over 100,000 tonnes of acids and other chemicals into the atmosphere every year from its chimneys. These chemicals cause bronchitis and other illnesses, and acid rain, caused in part at least by our coal-burning power stations, is one of our biggest environmental problems.
Well, when you compare, say, nuclear with petrochemical or nuclear with coal mining, the difficulty you have is that coal mining is an established industry in this country. In fact, undoubtedly an industry that people still have a lot of affection for, even though it's a very dangerous industry in terms of deaths per unit of energy produced. Likewise, the petrochemical industry, although it's not so long lived in the British industrial history, nevertheless is seen by the public as something which is worthwhile and something which has a great value to the economy. So, though there are real dangers in both these industries, people accept these dangers either because they're familiar and therefore become part of their day-to-day culture, or because they see them as worthwhile in terms of the well-being of the British nation. But when it comes to nuclear, then the deaths and the injury associated with the nuclear industry is so much greater, or potentially, and people believe them to be so much more catastrophic that they find that these levels of risk are too great to take. And at the same time, they're no longer sure that nuclear power is a necessary part of the energy strategy of Britain. And I think it's a lack or loss of faith in the benefits attributable to nuclear power which is causing the industry its greatest headache at the present time.
So what are the benefits claimed for nuclear power? Well, in general, it's claimed to be cheaper than other forms of making electricity, although the margin is a narrow one. It's environmentally cleaner than either coal or oil-burning power stations. And it can generate vast amounts of power from relatively small amounts of fuel. Instead of a never-ending string of coal trains, the fuel for a nuclear power station turns up once a week on the back of a lorry.
For the moment, of course, we've got a substantial amount of nuclear generation in the UK, about 20%, that 1 in every 5 light bulbs. It's easily our most economic form of generation, so if we lost that ability, the very short-term effect would be some difficulty keeping the lights on, but I dare say we'd cope. But more importantly, a significant increase in consumer prices. If we lost all our nuclear generation, for example, it would cost us well over £500 million a year to replace that output.
The historic record shows that in general, nuclear power has not been significantly cheaper than coal-fired power, but that it hasn't been significantly more expensive either. The thing is fairly well balanced. The idea that nuclear power would be economically much superior to coal firing has always been a prospective matter. It's always been what should happen in the future, and one has to say it hasn't quite happened yet.
The salient feature of electrical power, is that the operator, say for example a CGB, supplies the power, but we, the public, set the demand. So I don't know what channel this is going on, but if it was Coronation Street or the EastEnders, that covers both sides, in the interval at the end of the programme, everyone switches on their kettle, bang, suddenly there's a demand on the CGB to provide power. Now you need power stations for that. Economic power stations are very big power stations, and to cover for contingencies of breakdowns, you need to link all those power stations together on a national grid. So that's one way. Alternate means of power are relatively small sections of power, like windmills, 160 kilowatt, tidal barriers, 30 megawatt, things like that. Not only can you not generate large units of power, you cannot generate high potentials of power, high voltages, high levels of power. So alternate sources of power are not feasible on a large scale.
Well, I think this country is capable of indulging in a non-nuclear future. The sizable inquiry took evidence, quite significant evidence, that a major conservation investment, particularly in the technology of electricity reduction, that is more efficient electricity using appliances, could well have an economic boosting effect and at the same time reduce the need for new reactors, or in fact electricity generating generally. I think therefore the argument is very much up for grabs that we could indulge not just in a non-nuclear strategy but in a significant reduction in future electricity generating capacity.
Meanwhile, just a few miles across the channel, the pylons march off across the countryside in all directions from their nuclear power stations. 43 reactors built, 19 more are building. France is the world's leading nuclear power economy. In fact, it's fast becoming the major exporter of electricity in Europe, since it can generate far more than it needs and it can sell it more cheaply than its neighbours can make it. And all this, it seems, with scarcely a ripple of public resistance to the idea of an economy that is a hostage to nuclear power. That power station you can just see over the rooftops behind me is at Gravelines on the northern coast of France. It happens to be the biggest nuclear power station in the world. It puts out 5,400 million watts. It supplies the whole of northern France, northern Paris. It will soon be supplying 2,000 million watts into the UK grid. It's a real manifestation, if you like, of France's immense commitment to nuclear power. Something over 60% of this country's electricity now comes from atomic sources. I'm sure many nuclear industries around the world look at France with envy and say, that's the way to do it. No shilly-shallying, no mucking around. Just get on and build the nuclear power stations and let them run. And it's worth asking, perhaps, how and why France has gone so far, so rapidly into nuclear power.
Now, one of the reasons that has been speculated for that is that France has a very different tradition. It has been a country that has experienced, within 100 years, 3 major incursions across its national borders. The 1870 Franco-Prussian War, 1914-18 War, last war. National pride was very much at stake. There was a general failure of its technology. And in the course of post-war rebuilding, technological advance was very much built into national pride, French sovereignism, hence the development of its own independent nuclear deterrent pretty much taking its own route in recovering its pride, and nuclear energy seems to have fitted into that mould. In Britain, it's been a very different situation. I heard it speculated that our patriotism is most manifest in whether we win the Ashes or the World Cup. So we don't seem to have put our pride behind the sort of science and technology.
Well, I think this country, curiously, has had a very ambivalent attitude towards science, industry and technology. All the way through from the whole period of the Industrial Revolution, there was a very strong support for industrial prowess. But at the same time, people were moving away from industry even 100 years ago. And more recently, it's become very evident that this country has a curious kind of anti-industrial bias. It's not particularly anti-technology, but it actually likes to have the benefits of technology without getting involved with the messiness of the whole phenomenon. So rather see the Japanese or the West Germans doing it than ourselves, and somehow we can muddle along without it. I think it's a general feeling it's about.
Nuclear power, of course, has developed in Britain and the Soviet Union. Very much to do with centralised control, very, very large facilities, inaccessible to the general public, esoteric skills and knowledge. It's very much to do with centralised, remote centralised control. And if you're a person who's in favour of very decentralised, small-scale, person-to-person, face-to-face, warm human relations, a world in which that's the dominant pattern, then you'll be acting quite rationally if you pick out the risks in such a way as to show that they're not really acceptable and they bring all kinds of awful things with them. So, because you will be using those risks to oppose a technology that you feel, and probably fairly correctly in that instance, is going to usher in a social world that's much less to your liking than the one you would like.
Whatever social world is ushered in, it will be our children who have to live in it. What is their view of nuclear power? Well, perhaps surprisingly, because for them, of course, the bombs that fell on Japan in August 1945 are as much a historical event as Trafalgar or the Crimea or the battles of the Somme. They still see nuclear power in military terms. Asked to draw it, they came up with pictures of bombs and rockets and barbed wire fences. The nuclear power industry is not simply a younger industry than the coal-burning one. It seems to live permanently in the shadow of its origins. From Hiroshima to Chernobyl is just 41 years, little more than half a lifetime. During that period, the nuclear power industry has been fueled by a quest for cheap, abundant and environmentally benign energy. It's never really achieved that target. It's been said to be cheaper than coal and oil, but never by a sufficiently large margin. It has a good environmental record, but all that's been swept aside by events such as Windscale and 3 Mile Island, and more recently, of course, Chernobyl. But the question is, project ourselves on the next 40 years, to 2025, say, and will Chernobyl be seen as a major watershed, the beginning of the end for the nuclear power industry, or as simply a hiccup in a long continuing story, a cause perhaps for a major rethink of reactor design? It's still far too early to tell. We know so little about what went on. But the lessons yet to be learned from Chernobyl may be so terrible that many nations currently committed to a nuclear future may be persuaded to abandon it, whatever the cost. But at the end of this long march through the nuclear scene, one impression prevails above all, and that is that the nuclear power industry has never really been able to break the shackles imposed upon it by what happened at Hiroshima. However cool and rational the assessments of the scientists, the fundamental emotional public response remains. The risk seems altogether too great for the benefit. And in the end, that public response may prevail over the assessments of the scientists.